That's all I have for today. Thank you so much, and I'm happy to take any questions.
It sounds like we might be recorded, so let's.
Hi. Sure. Which one in particular?
Hello. Yeah, the base latency is 1.5 to 2 times the other protocol. So it gives me pause to say maybe you're just waiting a much longer time period. So the tail latency might be 1000x better, but for 95% of the cases, the base latency is much lower. And if you take specific scenarios like maybe financial trading systems, that marginal latency actually makes a huge difference.
Yeah, so that's a good point. So one thing is like we are limited by like current hardware where there's like it's difficult to achieve like this clock sync because even the state-of-the-art protocols like give like a best case effort. So when we did this in our cluster at my university, we had to use like a hacky workaround where we had a signal generator that is basically pinging, sending signals to the replicas in constant intervals. And because of that limitation, the clock sync guarantee is actually like a couple of microseconds. So because of that, we had to adjust the waiting period to be longer. But we see this not as like a fundamental limitation of our work, but if, for example, modern or like future hardware can be better at synchronizing the clocks, then you could also have like lower median latency. And also like this is adjustable. Like we went with this particular case since we wanted to optimize more for the tail latency, but you could still adjust because as I said, the replicas are sending in a round robin fashion. So they have, let's say, a slot of maybe 10 microseconds for each replica. So you could shorten or expand it as needed. Does that help answer your question?
So if I design a very dumb protocol where I'm waiting for k+1 replicas in a quorum to actually respond, the probability that I would actually hear back from a bunch of replicas beyond a certain k, even if it is half RTT, it gives you a huge gain that it allows you to commit faster, especially in quorum. So 1.5 times RTT gives you enormous advantage that it's an apples to oranges comparison is my take on the tail latency part.
Yeah, I mean like so for our particular I guess algorithm, we wanted to optimize more for the throughput and the tail latency as opposed to the median latency. So there could be applications where the most important thing is the median latency, maybe in trading as you had mentioned. But I mean, I'm happy to like discuss more offline about like how, like for example, this work could be modified to optimize also for the median latency.
Yeah. Other questions? So, actually, I had just one clarifying question. You mentioned that when the clocks are perfectly synchronized, that then it's not the queuing isn't stable, whereas having slightly asynchronous would achieve stability. I was just unclear why perfectly synchronized clocks would not have stability.
Sorry, can you repeat?
You had a slide where you said that perfectly synchronized clocks, you wouldn't have stability. And then when you have these slightly asynchronous clocks, that can then achieve stability. And I was unclear why fully synchronized does not have stability.
Oh, I did not mean to say stability specifically. I meant to say that, so in this model, it assumes that key drops cannot happen or packet drops cannot happen at all. So my point was like, it could be that this model can somehow prevent queuing magically, but then in the physical layer, packets can still get dropped. And this does not take that into account. Additionally, it's not, I guess, stable in the sense that it just assumes there's some hypothetical upper bound, for example, on the amount of time it takes for a text to get delivered. but in practice, without knowing how much data you're about to send on the network, and if the capacity in actual network link will be like limited, so it's going to exceed that it's going to exceed that bound. That's kind of what I.
Okay. And one more question. These systems, I presume the replicas are usually co-located in some sense. Like you're not trying to build something where they're distributed across the wide area.
Yeah, so for now, at least as a starting point, we focused on, as I was saying, a single tenant data center. But I would be like very interested in doing work which kind of tries to extend it to like a geo-replicated setting, because there's a lot of clock sync protocols now which are getting better at like synchronizing clocks across data centers too.
All right, let's thank Karan.
Thank you, everyone.
Next up is Cyrus Illick. You have a laptop or? So Cyrus is a third-year PhD student at Columbia, advised by the illustrious Dan Rubenstein and the other guy, Vishal Misra, who couldn't be here today. So he'll talk about making congestion control algorithms insensitive to underlying propagation delays.
And you want
I'll stand here.
Okay.
And good morning. I'm Cyrus. I'll be talking about our work making congestion control algorithms insensitive to underlying propagation delays. So congestion control algorithms, or CCAs, manage the sending rates of network end hosts to prevent congestion collapse and to control how available capacity is shared between competing streams of traffic. The original mechanism was proposed back in 1988, and since then, as the internet has grown in capacity and number of users, today there are many different CCAs, some of which are designed for different network settings, for example, in data centers or over wide area networks, and some of which are designed to optimize for different performance objectives, for example, like achieving lower latency or higher utilization. The way that CCAs manage the sending rates of competing streams of traffic depend on the network settings that these streams of traffic are in. So for example, in this scenario, 3 users are simultaneously requesting data from the internet while sharing a 50 megabit per second bottleneck. The way that their rates are allocated is going to depend on the properties of the bottleneck that they share, and it's going to depend on the number of competing users. It's also going to depend on the applications themselves, like the relative throughput needs to achieve a good quality of experience. And then in settings where the different applications have different workloads and choose to utilize different CCAs, then the differences in their CCAs will also impact the relative rates that the flows achieve. Deciding how these different CCAs should compete with each other depends on your view of internet fairness. The reality today is that a lot of applications will choose to use the CCAs that best suit their own needs rather than the CCAs that are necessarily like the most fair. And in our work, we're not taking a strong stance on the definition or importance of internet fairness. And instead, we're just proposing a more broad notion of predictability. And that ideally, an allocation of rates between a set of competing applications should be predictable as a function of the decisions made by those applications and the properties of the bottleneck that they share. And the allocation of rates should ideally not be dependent on any extraneous network factors. And in particular for this talk is the extraneous network factor of end-to-end propagation delay. As a refresher, propagation delay is just the minimum round trip time along a network path, where round trip time is the time it takes for a packet to go from the sender to the receiver and for the acknowledgement of that packet to return to the sender. When CCAs are sensitive to propagation delay, we view performance as unpredictable because an allocation of rates between a set of competing applications will vary as we vary the respective propagation delays. And on the other hand, if CCAs are insensitive to propagation delay, performance becomes more predictable because an allocation of rates between a set of competing applications can be met more consistently across different network settings with different propagation delays. It is well known that the most popular CCAs used today are sensitive to propagation delay. Cubic has the property where a shorter delayed cubic flow will converge to a larger share of capacity, and BBR has the reverse property where a larger delayed flow will converge to a larger share of capacity. There are some CCAs which are designed so that if all competing flows are using the same CCA, they can converge to equal rates regardless of any difference in their propagation delays. But this property requires that all of the flows use the same CCA. And if we introduce another flow that is using a different CCA, then the allocation of rates can again become dependent on like the specific propagation delays that each flow has. Another difficulty in these heterogeneous settings, where the competing flows are using different CCAs, is that even just measuring the impact of propagation delay becomes more difficult. So here we have two competing flows which are using two different CCAs, and they have different propagation delays. And if we measure the rate between these two flows, it is unclear how much the difference in their rate is the result of the difference in their propagation delays and how much was impacted by the different CCAs that the flows are utilizing. We also can't rely on what we know about these CCAs in homogeneous settings to inform us of what's going to happen in these heterogeneous cases. So here we have a cubic flow competing against a BBR flow where both have 12 milliseconds of propagation delay. In this case, the cubic flow converges to a rate of 25 megabits per second. But if we increase the propagation delay of the cubic flow, we observe that its allocated rate actually increases, which contradicts what we might expect from homogeneous settings where a shorter delayed cubic flow would achieve a larger share of capacity. So we need to come up with a new way to measure the impact of propagation delay in these heterogeneous settings. And we'd like to be able to do this without comparing the rates between competing flows, which might have different application workloads or different performance needs. And so really what we're looking for is a way to quantify this notion of predictability with respect to variations in propagation delay. And to do this, we can focus on each flow individually, and then we can observe the rate that that flow achieves over different configurations of propagation delay. And then we can measure sensitivity by looking at the maximum and minimum rate that that flow achieved over the full range of possible propagation delays. And the reason we want to focus on a range of propagation delays is that different network settings are going to have different ranges on the like possible or probable propagation delays. For example, in a data center, the propagation delays are going to vary in a much smaller range than the propagation delays that will occur in wide area networks. And it's even possible that different competing flows within the mix will have different ranges on their possible propagation delays. You can think of content coming from a CDN node having a relatively narrow range of propagation delays as it competes with other streams of traffic whose propagation delays vary in a much larger range. Formally, to measure delay sensitivity, we fix the set of competing applications and the properties of the bottleneck that they share, and then we specify a range of possible propagation delay configurations. We measure delay sensitivity as the log ratio between the maximum and minimum rate achieved over this full range of propagation delays. We do this for each flow individually. To visualize this, in this figure, we are plotting the sensitivity of this first BBR flow as it competes against another BBR flow over a 200 megabit per second bottleneck. We plot the sensitivity of that BBR flow in different ranges of propagation delay. We vary the minimum delay of the range on the x-axis and the maximum delay of the range on the y-axis. And then we can observe how sensitive this BBR flow is if the propagation delays of both competing flows fall between 16 and 48 milliseconds. And we can compare this to how sensitive the BBR flow would be if the propagation delays fell between 8 and 16 milliseconds. Now, before getting into our proposed solution to reduce this sensitivity, I want to just illustrate the impact of the sensitivity on real-world application performance. So here we have a 4K YouTube video being played, which is sharing a 50 megabit per second bottleneck with a OneDrive file download. And over experiments, we find that the sensitivity of this YouTube video to the range of propagation delays between 7 and 37 milliseconds, the YouTube video has a sensitivity of 0.7, which means that the rate that that YouTube video achieves varies by a factor of like 1.6 over the different configurations within this range. And with this level of sensitivity, the performance is unpredictable. In one configuration within this range, where the YouTube video has 37 milliseconds of propagation delay, and the OneDrive file download has 12, over 3 repeated trials, we can see a relatively low amount of stall time when playing the YouTube video, like the time that the video is paused for rebuffering. But if we look at a different configuration within this range, where now the YouTube video has 12 milliseconds of propagation delay, and the OneDrive file download has 37, we can observe a significantly larger amount of stall time, like the time that the video is paused, just by changing the configuration of propagation delay. So we're noting that like this is just that the configuration of propagation delay is now a contributor to how these competing applications are sharing this bottleneck. And the performance is not predictable just by the needs and the decisions made by these applications. Our goal is to make CCAs insensitive to propagation delays for the range of practical propagation delays that these flows are competing in. And ideally, we'd like to be able to do this without requiring that all competing flows use the same CCA or introducing any new complicated mechanisms within the CCA's control loop. And our idea is if we could get all competing flows to agree on some larger propagation delay lambda, and then artificially increase the propagation delay that the CCA perceives it is operating on, then regardless of what the natural propagation delays are, the competing flows will operate insensitive to any variations in their natural propagation delays. So we can trick a CCA into thinking it has a larger propagation delay simply by adding delay before sending or receiving packets at either end host. But when we add delay, we want to be careful to not add any delay on actual application data. So we don't want to add any like data latency. But if we add delay by holding the acknowledgements of packets at the sender for a fixed period of time before releasing them to the CCA to be processed, then we can increase the total minimum round trip time perceived by the CCA, or the like propagation delay perceived by the CCA, without adding any additional data latency. To visualize this, in this figure, we're showing the impact of adding 60 milliseconds of fixed delay at these 4 different locations. And we can observe that as long as we are adding this delay along the acknowledgement path, the full perceived total minimum round trip time is increased, but the data latency is preserved. It is also important that we're equalizing propagation delay and not full round trip time. This way, delay-based CCAs like BBR can still use variations in congestive delay as a congestion signal and can operate normally once we've inflated propagation delay up to this point lambda. We can observe when we implement this solution that the propagation delay sensitivity that we observed for BBR earlier is effectively reduced to 0 when we set the point of equalization to be 100 milliseconds. And there's more results in the paper on different settings. The reason that we are equalizing propagation delay is to make it so the way that applications compete with each other is more predictable. But we only want to do this in settings where adding this propagation delay is not going to negatively impact the performance of the application if it was operating alone. So generally speaking, for long-lived flows, adding a reasonable amount of propagation delay should not noticeably or negatively impact the performance of that application. So for example, a file download with 10 milliseconds of propagation delay should take roughly the same amount of time as a file download with 100 milliseconds of propagation delay. And on the other hand, for short-lived flows, adding some amount of propagation delay could negatively impact the performance of that flow. But in this case, for short-lived flows, they're not lasting long enough to respond to congestion signals and to converge to respective rates when they're sharing a bottleneck. And so we really don't need to, and we shouldn't use an equalization solution in this setting. And then lastly, so far we've been talking about equalizing propagation delay as a way to reduce the sensitivity and variations to propagation delay. But we can, in even simpler ways, use artificial delay to reduce sensitivity simply by altering or changing the perceived range of propagation delays that competing flows are operating on. So in this figure, we are plotting the sensitivity of 4 competing flows, which are using 4 different CCAs over the range of propagation delays between 10 and 30 milliseconds. And then we're comparing this to when we add 50 milliseconds of fixed delay to all 4 competing flows, regardless of what their natural propagation delays are. And this effectively changes the range of propagation delays to being between 60 and 80 milliseconds. We can observe that just by changing the proportional size of this range as we increase it, that the sensitivity of all 4 competing flows goes down. And then finally, if we are able to also reduce the range, so here we're looking at the sensitivity of 4 loss-based CCAs competing over the range between 10 and 30 milliseconds. And we're comparing this to when we have increased the effective range to being between 35 and 45 milliseconds. And we can observe again that reducing the range is able to reduce the sensitivity for all competing flows. So in this talk, we discussed how these heterogeneous settings where the competing flows have different CCAs or maybe have different workloads makes it more difficult to both measure and address the impact of propagation delay. We propose delay sensitivity as a way to quantify this notion of predictability with respect to variations in propagation delay. And this lets us measure the impact of propagation delay in these heterogeneous settings. And then we suggested using artificial delay or added delay as a way to reduce this sensitivity in these heterogeneous settings. All right, thank you.
Any questions? I'm not going to ask a question. I'm an author on the paper. Yeah.
Hi, very nice slides too in terms of the animation stuff. 2 questions. One is if the bottleneck moves around, what is happening there? So you have an application.
Are you saying like if we change what the bottleneck properties are?
So that during the life of a connection, the bottleneck at some point is the access length somewhere. Sometimes it's somewhere else in the network.
Okay, I see. So I would say that like this is that when we say we want to equalize propagation delay for this setting, we would assume that we're actually equalizing it not for the full lifetime of the flow, but it will repeatedly update this estimate in the same way that a lot of CCAs do this.
Okay.
And so it should, like, if there is a switch in the network path,
yeah,
we actively monitor what the estimate of the propagation delay is, and then we can readjust what the added delay is to equalize.
The other question has to do with, so if you think of sort of CCAs, machine learned CCAs that can react very, very fast to changing network conditions in unpredictable, in strange ways. How does this sort of impact?
Can you repeat that one more time?
So if you have CCAs that are using sort of machine learning techniques,
okay, yeah,
to decide what the sending rate should be at any point in time, how does it, and that can change pretty much. Like
are you talking about the machine learning CCAs that are designed like the learning ones, like Aora or Orca, or those ones?
Yeah.
I mean, like, this is ideally this solution should be somewhat separate to like the actual CCA itself, because we're implementing this outside of the CCA's control loop. Yeah. That ideally it should be the case that with any of these different CCAs, including like the machine learning ones, that we're equalizing this propagation delay outside of the CCA. So then the CCAs can be designed for whatever performance metrics or performance objectives, and then now it will be over the space of equalized propagation, if that makes sense.
Okay. Right. Okay. Yeah.
Any other questions?
Yeah, really interesting idea. I was curious, like I may have missed this, but what is the estimator for the equalized propagation delay look like? So if I have like end flows,
how we estimate like the natural propagation delay to then equalize it?
Sure. Or like on the bottleneck link, how do the end flows competing on that link know?
So we base it based on how a lot of the delay-based CCAs make this estimate anyway, which is that we'll take the minimum round trip time observed over the last 10 seconds or 5 seconds. It depends. But and then it's just like, especially with these delay-based CCAs, they have mechanisms built in which will periodically reduce the sending rate to take out any potential congestive delay, which would make the measure of propagation delay more reliable over a period of time. And the reason we don't want to have it over the full lifetime is for the cases where the network path has changed and you want to be able to update this.
Right, makes sense. So that gives you the minimum propagation delay.
Yeah.
So how do you snap up to sort of the maximum among like n of them?
Oh, how are we choosing the point of equalization?
Yeah.
Okay, this is actually more of a future work question, which is that we are in our experiments assuming that we have all agreed on some point. So let's say like there is n competing flows, and we'll just say, okay, assume all of them have already agreed on some larger propagation delay. So we use, as an example, a lot of the time, 100 milliseconds at that point. That it would just, it's more about how you would go about choosing what that optimal point is. You don't necessarily have to have it larger than any possible propagation delay, because as long as you're capturing the bulk of propagation delays, you still maybe will have a range of different propagation delays, because some might be larger than that point lambda. You still will have effectively reduced the range. But yeah, that is.
Yeah, absolutely. No, that makes perfect sense. I would just, I think that is definitely an interesting question, because one of the things you would like to have with CCAs is to have this like parameter freeness, where you don't want to sort of parameterize like a CCA that is being, I'm saying like, oh, I'm using this in a particular setting where my maximum propagation delay is like such and such. And so it'd be really interesting to see if you can sort of compute this in band somehow without having to rely on like hard-coded parameters.
Completely agree. I mean, yeah, that's the other thing, is that if you could agree on some point like this, then you could think about how CCAs could be designed specifically for that, like how you maybe would tweak the design or the parameters of the CCA so that it performs at that point of equalization.
Cool, thank you.
Any other questions? I would just add, my perspective on that question is you're operating in some network environment and you have some prediction of what the allowable set of propagation delays in that environment might be. And one idea is you just choose the maximum of that. So if you're operating in a data center, we call it lambda. You could choose a very, very small lambda. If you're in the wide area, maybe lambda should be like 200 milliseconds. If you're operating in space networks, outer space networks, then maybe lambda has to be 10 seconds or something very large. But that's still something we're interested in exploring. So, any other questions? Okay, thanks, Cyrus.
Thank you.
Okay, our next speaker is Sata Sengupta. He's a final year PhD student at Princeton, advised by Jen Rexford. He works at the intersection of internet measurements and programmable networks. Recent focus on applications to video conferencing and network security. Sata is currently on the market for academic positions. And again, with respect to most conferences, I'm hoping we're going to have more discussion. Otherwise, I'm going to make you guys watch a bunch of videos. So feel free to ask any questions, clarifications, anything you want. It's okay to be controversial. Again, the NINES was supposed to be a conference where papers are not just formulating well understood processes. It's, considering something outside the box. So please feel free to ask and be critical.
Awesome. Thanks so much, Dan. All right, so today I'm going to present our system HIDE, which leverages passive data plane telemetry to mitigate long-distance BGP hijacks. The core idea is really to use minimum round-trip time, the change in that, to detect and mitigate a specific subset of BGP hijacks. This is joint work with folks at Princeton and University of Virginia. BGP hijacks continue to be a menace, including outages in Cloudflare in 2024, millions of dollars lost in cryptocurrency theft in 2022, and many, many others. Just to give you a sense or give you a refresher of how these hijacks work, let's say there is a client in Princeton that's communicating with a US government website on the West Coast, and they are exchanging sensitive information. And now there is an attacker, say in Europe, who sort of announces the same IP prefix as the US government website and uses some tricks to make the route to itself look more attractive. And so now this sensitive information starts traveling to the attacker instead of the intended recipient. Now, there's a stealthy version of this attack where the attacker essentially forwards the sensitive information back to the intended recipient, hoping that neither the client nor the server notices that something nefarious is going on. In HIDE, our central idea is that we can detect such attacks using changes in propagation delay, which, as my previous author said, can be approximated by minimum round trip time. And so going back to our previous example, we see that if there is this kind of a reroute, then the data travels an extra 11,000 kilometers, which adds a lot to the minimum round trip time. And in our controlled experiments, we do see that there is this sudden surge in min-RTT, which is there when there is an attack and not there when there isn't an attack. This change in min-RTT, or the min-RTT itself, has to be measured at a vantage point that is close to either end, either close to the client or close to the server. Now, where does HIDE sit in terms of the prior work? BGP hijack defenses can broadly be divided into two kinds. One is proactive, the other is reactive. Proactive approaches are great, but they suffer from deployment challenges in the real world. They're not universally deployed yet. In terms of reactive solutions, a majority of them rely on control plane information, and they rely in turn heavily on BGP monitors. And so depending on where these monitors are placed, some attacks can be stealthy enough that they are actually never detected, or some others can eventually be detected, but enough time has passed that the attacker can actually cause real harm within that time. In terms of data plane approaches, there are active measurement-based approaches and passive measurement-based approaches. Active approaches rely on responsive endpoints, so they send probe traffic to responsive endpoints, and then wait for the replies and calculate RTT that way. But then this involves probe overhead in terms of traffic, and also require responsive endpoints, which may not always be there. Hybrid defenses sort of use a combination of control plane-based approaches and active measurement-based data plane approaches. So they do not really alleviate the limitations of either fully. HIDE lies squarely in the passive data plane-based solutions, which has remained underexplored so far in the literature. Now, HIDE is not really a silver bullet. It has several limitations. And the first one is related to scope. So RTT change is really highly location dependent. For example, if the attacker is in the UK and the victims are in the US, it's fairly easy to detect that attack. Versus if the attacker is in Canada, then it's really not that easy to detect that attack. Also, there's an issue related to accuracy because RTT tends to be a noisy signal even under normal circumstances. So for example, due to congestion or benign routing changes and so on and so forth. So HIDE is really not a general purpose hijack defense. However, it has several key advantages. One relates to scope. So for a specific subset of stealthy hijacks, which is the long distance subset, it's really good at detecting those attacks. The second one relates to speed because RTT changes are immediately visible at either end. So you can detect and mitigate almost instantly. Third is regards to accuracy. So in conjunction with other control plane based methods, HIDE can really provide an additional signal that can help you confirm or deny a suspected hijack. And then finally, by virtue of being in the data plane, and a network operator can perform fine-grained mitigation, which is per IP, as opposed to per prefix, which is the best control plane-based mitigation can do. So we argue in this paper that HIDE is a really useful tool to have in a network operator's toolkit. So on the one hand, we have the limitations, and on the other hand, we have the promise of HIDE. And so this leads us to ask two main research questions. One is with regards to feasibility. How feasible is it really to detect long-distance hijacks using just RTT? More specifically, we focus in this paper on cross-country attacks because a lot of them tend to be long distance. And also these are especially important because they're used in cyber warfare or in surveillance where one nation state tries to steal information from another. The second question relates to scalability. So how can we use this idea of change detection and propagation delay to scale to production scale traffic? So how do we build an always online scalable system? And so more specifically, how do you perform RTT change detection in a hardware amenable way? So first, the question about feasibility. So we define feasibility in the following specific way. Let's say these are the min RTT samples for a flow in time windows. And so we divide the space of RTT into three parts. The green part is what is observed to be the normal range of min RTTs during operation. So the top line essentially refers to the measured maximum min RTT during benign operation. The yellow part is a buffer that we call a surge threshold. And this really exists to absorb any new sort of normal variation in the min RTT during normal operation. And then finally, the red zone is where we start to suspect that this is an attack. And the bottom of that red zone is actually determined based on the minimum distance the attacker, the traffic needs to travel in order to go through the attacker, and the speed of light in optical fiber, which is roughly 200 kilometers per millisecond. So this is really based on physics. Now we come to the data sets that we use to evaluate feasibility. First, we take the Natural Earth data set, which has country border information for 258 countries around the world. And for each pair of countries, so say country A, attacker, country B, victim, we find the minimum perturbation and distance that A must introduce in order to launch a successful attack. And we call this the best case attack from the point of view of the attacker. So we have 258 multiplied by 257 best case attacks. And then for RTTs under normal operation, we collect data from two different data sets. One is from our own campus. We collect data for 7.5 million TCP flows, and from Google MLab, where we collect 4.3 million TCP flows. So here are our key observations, and I encourage you to read the paper for more details. So the first question we ask is, what percentage of cross-country best case attacks are actually defendable? And we find that the numbers are reasonably high. So for the campus data set, 91% of the attacks are defendable. For the MLab data set, 86% is defendable. And the difference between the two is explained by the fact that under normal conditions, the campus data tends to be less noisy than the MLab data. We also find that small and geographically isolated countries are easier to defend than other ones. So for example, New Zealand was one of the easiest countries to defend in our data set, as opposed to Russia, which was one of the hardest to defend. The second question we ask is, beyond just country borders, how far does the attacker actually need to be physically for it to be detected? And it really depends on the noise in the RTT, but the answer is roughly as far as the victims themselves. And so to give you an example, if a client is in New York and the server is in Vegas, then the attacker needs to be at least as far as Venezuela in order to be detected. So we come to the second question now, which is how do we then convert this idea into a hardware amenable change point detection system? So to give you a sense of the deployment setup that we have in mind, let's say there's a client inside, say, Princeton campus, there's a server, and at the campus or enterprise edge, the network operator is trying to defend against such attacks from a certain vantage point. And assuming that this is a programmable switch or a SmartNIC and so on, we can do the following. So let's say a stream of packets comes in and goes back out through this switch, and the switch does normal forwarding as it would normally. In addition to that, it extracts the packet headers and then feeds it into an RTT measurement system, which is based on our work back in 2022 called DART. DART generates a stream of RTT samples, and then eventually HIDE comes in where it analyzes the samples in real time and performs change detection. And if there is an attack, then it installs relevant rules on the forwarding plane, either rate limiting the traffic or dropping the traffic, depending on how the network operator wants to use it. So how do we go from having RTT samples to really min RTT? And so we denoise sort of RTTs in the following ways. First, we calculate min RTTs in non-overlapping time windows. And then second, we aggregate the min RTTs across /24 prefixes, because a /24 prefix is the minimum subset of a prefix that an attacker can launch an attack on. And so to give you an example, let's say we have flow 1 and flow 2 on the left, represented in blue and red. And then you can see the green triangles on the right side at the bottom. So even if the RTTs are actually noisy to begin with, finally, when we apply these methods, they tend to look very stable. Second, the operator needs to provide some inputs. So essentially, for a target prefix that the operator is trying to protect, they need to provide what they think would be certain regions in the world that they suspect attacks could come from. And essentially, we compute the best case attack for an attacker from this combined area based on physics. And we call that threshold the absolute threshold. So that was about how to determine when to detect an attack. But now we need to know what happens under normal operation. And this is where the profiling phase comes in. So essentially, during normal operation, we do RTT profiling, where we keep an account of what is the measured maximum min RTT in time windows. And one good thing about this is that this can be done entirely in a hardware amenable way because we are just computing maxes and mins within windows. Then in the detection phase, we do min RTT change point detection in the following way, where let's say these are the min RTTs in time windows, and we see that the samples were in the green zone, and then suddenly we have a surge right up to the red zone. And so we have two approaches here. One is we say it's an attack the moment it hits the red zone, which would be the blue star there. We call this a two-window algorithm because we go from one window being in the green zone to another in the red zone. If we want even more confidence, we can wait a little bit longer and then wait until the next window, which is the red zone, to finally confirm that this is an attack, and that we would call the three-window algorithm. So to give you highlights of the evaluation, we collected all the US-based prefixes in our campus traffic, and we simulated optimal attacks from 257 non-US countries in the natural Earth data set. So first we asked the question, what percentage of attacks are defendable based on just the absolute threshold? And we find that 78% of those prefixes were defendable against 99% of the attacks, and then 99% of the prefixes were defendable against 75% of the attacks. Now, within those prefixes that are defendable based on the absolute threshold, we ask what percentage is defendable based on the surge threshold. And so, so to remind you, the surge threshold is essentially the buffer. And the longer we want the buffer to be, the lesser coverage we can have, essentially. So we find that for 99% of the prefixes, we can defend them against 91% attacks if we assume a buffer of 5 milliseconds. But if we want a lot more confidence, which is 25 milliseconds, let's say, we can only defend against 64% attacks. But what is the false positive rate when we try to defend these prefixes? And we see for a surge threshold of 5 milliseconds, the rate is 0.012%. And when we go up to 25 milliseconds, we almost eliminate all false positives. And then finally, what is the detection speed? It really depends on the rate of RTT generation, and which in turn depends on the data rate of the flow itself. But in general, in our data set, we find that the speed tends to be within tens to hundreds of milliseconds. With that, I come to the conclusion. We quantified the feasibility of RTT-based hijack detection in this work. We designed a system for scalable in-network detection. And then really, this starts to become very, very useful when we can combine HIDE with control plane-based methods that are already out there and doing really well. Thank you so much for listening.
Hi, thank you for the talk. It was really interesting. One thing I was curious. So if I understand properly, you pick your prefix in advance. So how can you control for instances where there's congestion on like a peering link, for example, and all of your prefixes are seeing this increase of RTT, not just this specific, like not just one prefix. So how do you like determine that this is just congestion versus this is an attack? Especially given that you wait very little time before you raise an alarm. Do you have some mechanism that compare all the prefixes jointly or not?
Yeah, that's a great question. We do not currently do that. Like we do not currently combine information from multiple prefixes. So to counter against such incidents where we have congestion delays that are pretty high quite high than normal, we have that buffer, that surge threshold. And the idea is the operator would have some idea about how much is normal to have in terms of congestion. Because you're looking at the min RTT, hopefully the operator has like some window to some room to play with, essentially. So yeah, so if the range within which congestion can happen is sort of overlaps with the range where the attacker can also be geographically, then we cannot really detect it.
Okay. I have a related question. So, did you look into the scenarios that cause the false positives?
The scenarios where there is false positives?
Did you look into those scenarios? What are those?
Oh, that's a great question. So the main kind of false positives that we see is when we operate with cellular networks where the access side has a huge amount of noise. And essentially, I did not go into details here. We sort of invented the 3-window algorithm in order to deal with a lot of those scenarios because we saw that waiting a little bit longer can actually give you an advantage. So it really reduces the false positive rate. Another thing I want to say is that in the paper, we actually do after the fact mitigation as well. So let's say you have a false positive. We first take some action immediately because let's say the traffic is sensitive, the network operator really doesn't want to chance anything. So we rate limit or drop, but then we send active probes out to keep an eye on how the min RTT is looking over time. And if it reduces, then we actually unblock the prefix or undo whatever operation we did. We do have that mechanism as well.
So I had a very basic question. How do you measure RTT at your vantage point? Is it through the flow or is it by sending extra traffic?
No, it's through the flow. It's completely passive. So the data ACK matching, essentially.
How do you know that the ACK is actually going through the same vantage point? The reverse path need not match.
Right. So that is an assumption we make in the work, that we are close enough to either side. So let's say the gateway of the Princeton campus network does see data and ACK on the same sort of vantage point. There is one vantage point where it sees it. So there you can do this kind of defense. If you are too far away where the paths may not match, then you cannot have RTTs at line rate like that.
So let me think through like a slightly concocted but slightly realistic scenario. Mm-hmm. So let's take NYU as an example, right? A lot of students connect to NYU via the VPN, right? And if I'm actually switching between LTE on my phone and Wi-Fi in my house, as an example, and then the traffic is tunneled via a VPN to an NYU gateway, and you're running your algorithm at the gateway, you can actually see massive RTT differences even for a single flow. How does your system handle that?
Do you mean across the two kinds of connections, so Wi-Fi and LTE?
So you don't know that it's Wi-Fi or LTE, but because it's a VPN, so for example, let's say I'm on a WhatsApp call and I'm actually tunneling it through a VPN gateway, right? So for example, if you live in the Middle East, even to take a WhatsApp call, most people use VPNs to external servers to even make WhatsApp work. So if you're running your stuff at the gateway, and let's say I have a Google Fi kind of service, which allows me to switch from LTE to Wi-Fi automatically, even for normal calls on the fly, then basically you will be observing massive RTT variations for a genuine flow.
Yeah, that's a great question. So the first, I'll answer that in two parts. The first one is that if the min RTT is too high to begin with because of the tunneling, because maybe you're connecting from a far end of the world, then we will not try to protect against that prefix, protect that prefix anyway, because we cannot realistically do that because the min RTT is like too far, such that there is a lot of overlap with wherever that attacker could be in the world. The second would be that's exactly why we want to combine hide with control plane best methods as well. Because there can be cases where even under normal circumstances, as you're pointing out, that there can be an RTT surge, which can look very much like an attack because there is a switch between Wi-Fi and LTE. And we may falsely conclude that it's an attack. But if there is more information from the control plane that the network operator has, then potentially we could try and mitigate that, like undo whatever the suspicion is essentially, or the mitigation strategy is.
Actually, one quick question. You mentioned this notion of defendable, and I was just a little unclear. Maybe just go over it again. You're identifying, but then you're also claiming some can be protected against and some cannot. What's the distinction?
So first, we want to profile the min RTTs of a particular prefix, and then see whether that overlaps with the minimum RTT physically possible across the attackers. If there is overlap, we don't even try to, it's not defendable. That prefix cannot be defended against those attackers. So that's out. The second thing is, does the min RTT vary a lot during normal operation? That tends to happen a lot with cellular networks, for example. So if it varies so much that you cannot realistically detect a surge, then also it is not defendable. And that's why the surge threshold-based defendability is there. So only the prefixes that are defendable after those two limitations are put in place are the ones we try to then protect against. And that's where the evaluation comes in, the rest of the evaluation comes in. Does that clarify it a bit? Yeah, awesome, thank you.
Sorry, one more question.
Yeah, of course.
You had those green, yellow, and red intervals. And you said one way to achieve greater confidence is to sample for longer, just to see whether you're actually in one of those intervals. But also, how do you determine where to set the green region versus the yellow versus the red?
Yeah, that's a great question. There's no exact science there. I mean, we try with various thresholds in the paper, and we say, like, you can either look at percentage in terms of what is the percentage of rise in min RTT, or actually absolute numbers make more sense because then you're saying, okay, what about I try 1,000 kilometers versus 10,000 kilometers in terms of geography? But really it would depend. It's a trade-off between what the network operator knows about its own system, about its own traffic, and where it suspects the attacks could come from out in the world. So yeah, there is no exact answer, but that's kind of framework.
Any other questions? Okay, let's thank the speaker again.
Thank you.
And our final talk will be given by Walter Willender. And in case you were having trouble with my trivia question in the beginning, Walter is the person who was a PhD student a long time ago and graduated from ETH Zurich in operations research and industrial engineering from Cornell University. He's currently professor of practice in CS at Northwestern, also has a courtesy appointment at University of Oregon. He's retired from Nixon, which is a Princeton-based cybersecurity company where he was chief scientist since 2013. Before Nixon, he worked at AT&T Labs Research in Florham Park and at Bellcore. Also, when I was a student, I knew Walter. He was one of the, I don't know if I'll say discoverers or rediscoverers of self-similarity and the fact that networking traffic has this self-similar behavior. So there were some really fundamental papers that Walter led back then. So, oh, there is a copy on it.
It's going to take me a few minutes to.
Just, yeah, thanks, then. It shouldn't be here.
Just a pod after all.
The market.
Oh, I guess while we're setting up, let me just add, the session ends, I think 10:45. So we should have some additional Slack time. I don't think we'll have like an official panel, but we can try to coalesce the various talks and just ask additional questions in sort of like a equivalent of like a panel-like setting. One general question you can always ask is, why did this paper belong in NINES? Why wasn't it sent or accepted or considered at your typical SIGCOMM, NSDI, Sigmetrics, Infocom, et cetera, et cetera? Also, think about what you might want to say during the future research, existing research, outrageous opinions session, or you'll just have to listen to me bloviate for 20 minutes or so, or we'll just watch some more videos.
Dan, I have a suggestion.
Yes.
I think it'll be good for people to just introduce themselves.
Oh,
If possible.
Yeah, sure.
If there are small breaks, just
Sure.
pass the mic around. And
okay. Start with you.
yeah, I'm Lakshmi from NYU.
That's here. Let's see if this works.
Okay, Dennis, also from NYU, second year PhD student.
Okay. And are you going to walk?
Lakshmi, what are you? You're a
Are you
third year
walk around?
PhD student?
Let me put a mic on you then.
Fourth year? Okay.
Okay, you stay here. Okay.
I'm Carson from Columbia. I'm a second year PhD student with Ethan Cass Bassett.
Hi, I'm Sunny. I'm a first year PhD student with Henning Schulzford.
I'm Andy, second year PhD student at UPenn.
Okay, why don't we'll stop for now. We'll finish the process. Everybody has to return to their seats after the coffee break so we don't interrupt the flow. Walter, please take it away.
All right, so this is something quite different. And it's something that has some history, but there is also very new stuff here, so it's a combination. There's more to internet invariance than meets the eye. So what's the high-level motivation? So we sort of all understand that the internet is a very highly dynamic system, moving target. And we have seen slides before in terms of protocols are developed pretty much on a constant rate. Here it's indicating even at an increasing rate over time in terms of RFCs. Applications come along, industries come along out of nowhere and become multi-million, billion industries in very short periods of times. And of course, there is also this constant effort to get access to these scarce resources like AS numbers. And so in the midst of all these ongoing dynamics, we as researchers sort of sometimes should ask ourselves, how can we ensure long-term relevance of our research when everything is changing? And so there has been 25 years ago a paper by Sally Floyd, Ron Paxson, sort of suggested that in order to sort of do something solid where you build something around something that doesn't change, look for something that's called internet invariants. Internet invariants are facets of internet behavior that don't change over time, that you find anywhere in the network where you do measurements and under all different kinds of network conditions. So do we have such invariants? And if so, then the question comes, we start with sort of an observed phenomenon that's related to such an invariant and ask this question: is this phenomena an indication of some underlying design principle in the internet? So this is sort of a more profound approach to understanding, internet invariants or statistical phenomena that people measure in the data that they collect from the internet. And the real question there is always, you observe something. The question is, does that observation indicate some deeper underlying design principle that people have either followed implicitly or explicitly? And so there are sort of two types of invariants that I want to focus on. One is historical, one is new. The historical one is the temporal aspect. So you're sitting on a link in the internet and you measure the packets that go by some period of time. You get number of packets or bytes per time unit. That's your time series. That's a temporal aspect. And then there is another aspect there. If you sit on a link in the network and you watch, you consider the set of IP addresses that you observe over a period of time that go by. That's a set of IP addresses out of the largest base of IP4 or IPv6. What do we observe on the temporal side? What do we observe sort of phenomenon on the spatial side? So talk is separated into two pieces. First, I talk about the temporal aspect, and then temporal aspect is sort of mostly historic, but it's still sort of relevant. So, okay. Sorry, is this better? Okay. So the temporal aspect goes back, 30 years, and has been observed again and again. And whether you call it self-similar or fractal or whatever, it's just this illustration of if you measure traffic at different timescales, it looks the same. So then the question is, where does this come from? And then there was this piece of work that sort of says this traffic on this link that looks self-similar or fractal in nature is the superposition of lots of independent on-off burst processes, where each one of them has this property that the burst sizes and the silent periods have heavy-tailed distributions. So heavy-tail means high variance, high variability. You see flow sizes that are large, and you see flow sizes, many flows, that are very short. So this is the mice-elephant picture of internet traffic. That's, has been observed for the last 30 years, pretty much anywhere in the network. And then the mathematics sort of says, okay, if you have this superposition of such flows, they produce self-similar scaling, but the critical entity that causes these things are these heavy-tailed flow sizes. So now the next question is, where do these heavy-tailed flow sizes come from? Again, there is sort of historical work that exists, but is not very well known, and that sort of says these heavy-tailed flow sizes really arise from a deliberate design principle that says if you want to design a website so that the user behavior optimizes the user behavior in terms of the user browses the website and finds the document that he or she looks for
and what's sort of the optimal way to design a network so that you make the user happy. You will design it in such a way that the website has lots of small items and a few large items. Again, the website itself will have this mice-elephant phenomena in terms of, and they are linked together in the website. So now we have sort of a situation where, we have, if you want to organize, if you have an application that aims at organizing information for human consumption, the internet still is, lots of stuff is still for human consumption. If you have such an application, it will produce heavy-tail flow sizes, and these heavy-tail flow sizes you will see on pretty much on any link in the network, which causes a self-similar scaling. So now you have sort of this, chain of arguments that says this phenomenon, statistical phenomenon of scaling of network traffic, can be traced back to a design principle that is really nowhere explicitly stated, but it's the design principle says, if you want your application to be successful, your application has to organize information for human consumption, and the web is a prime example of doing that. But then, of course, I come back to this. The end, you can sort of now ask, what is sort of causing? Why do we have to organize information for human consumption? What is the constraining factor to do that? But at this point, it's an example of, you certainly can sort of say the designers of the internet didn't design the internet to have self-similar traffic. It just occurs out of this underlying design principle that's really nowhere stated. And then this is then the second aspect of the internet traffic, and that's the spatial aspect. So here I show you the IPv4 space using the Hilbert curve representation. And what I show you is sort of a massive zoom in on finer and finer granularity. So I show you a bunch of /8s on a finer granularity, and then that bunch of /12s on finer granularity, and so on. And what you see is that, a burst at one granularity or a cluster at one granularity is made up of subclusters. So what the empirical observation of IP addresses that you observe on a link in a network, what it shows is this pronounced cluster within cluster property that mathematically can be described as multifractal scaling. And so again, here we have a phenomena that sort of comes out of empirical observations. And the question is, can we tie it? Can we find an underlying principle that causes this automatically? Or is it just an artifact? So the first step in this development was, again, a couple of years back, and that basically says, in order to get multifractal scaling, one well-known mathematical construction that produces multifractals is a cascade. In this case, a conservative cascade that does allocations of IP addresses in a mass-preserving way. Allocate a block, that block gets further allocated in terms of subblocks, but the mass is conserved. But that was sort of the state of the art 10 years ago. And the question is, can we go further in this where what causes, can we empirically demonstrate the conservative cascade? What are the entities that fall out from this empirical validation? And then can we come up with a organizing principle or a design principle that causes this multifractal scaling in IP addresses? When it comes to IP addresses, you always have to be a little bit careful in terms of, there are these notions of allocations, assignments, routed addresses, and then observed ones. So in order to observe an address on a link, the address has to be allocated, assigned, and routed. So the highest level of sort of importance here in terms of understanding IP addresses is the allocation process. And there is this empirical work that you can actually do and demonstrate that if you use whois data, you can demonstrate that the allocation process follows very naturally a conservative cascade. And that has been always sort of relatively intuitive to most people in terms of they know about IANA and they know about the regional internet registrars, and they know that each one of these registrars assigns addresses to the clients in those particular regions and so on. So this sort of intuition of a cascade construction has always been out there, but it has never sort of been validated with empirical data, with data from a whois database that is actually consistent with the cascade construction. And the unique aspect of this cascade construction is that, again, the allocated sizes turn out to be highly variable. What is being assigned, what is being allocated by these regional registers are blocks, and you look at the block sizes, and these block sizes are highly variable. Most of them are very small, some of them very large. And so again, now you're in sort of this setup where you have this conservative cascade that produces these heavy-tailed or highly variable allocations, block sizes. And the question is, where do they come from? Is there an underlying reason why allocated blocks have high variability? And there again, we go back to this sort of vehicle that we use in order to come up with a rational explanation, and that is the so-called highly optimized tolerance formulation of a constraint optimization problem that in this case takes the client requests as input. These requests must be satisfied by the regional registrars, and they have to be sort of be done in a way that's sort of consistent with what operators or these registrars ask the clients, or being asked to do, and that is make use of the space available that's given to them, and that minimizes the fragmentation of the allocation process. And then the uncertainty that this problem has to be, under which this problem has to be solved, is that you don't know the client requests in terms of the block sizes that they ask for. And if you solve this sort of constraint optimization problem, one of the results is that what falls out of an optimal allocation is that these optimal allocation sizes always have this heavy-tailed allocation size. So that the optimal allocation policy always ends up with allocations that have this high variability. And then you sort of go into, in this case, documents that are produced by IANA, and you actually see these statements of utilization efficiency should be observed when you do this allocation process, and fragmentation should be discouraged. So you have now explicitly stated indications that these two design principles, under this uncertainty that you don't know the allocation sizes that you have to allocate, these produce highly variable allocation block sizes. They are part of the cascade construction, which implies that the observed IP addresses have multifactor scaling. And again, it's an example where you certainly start out with this observed multifactor scaling of observed IP addresses is not something that the designers built in. That falls out of now is explanation of why this observed IP addresses are multifactor. So we have these two examples now of internet invariance that started out with empirical observations, and where we can now make arguments, reasonably plausible arguments for what causes these empirical observations and why they are permanent. And then this gets us to the end of the talk, and that is to say there is always this question. So as we have had applications, we had other applications, and in the current context, the typical question comes up, but future AI-based applications, won't they change everything? And again, if you sort of think of this design principle that says successful applications on the internet today still have to organize information for human consumption, then even these AI-based applications will have to obey this principle, otherwise they are not very useful or popular. You also can ask a question, why is it important that applications organize information for human consumption? So what is the bottleneck that we as humans have to consume information? Turns out the bottleneck is that we can process information, meaning absorb input, store it in a way so that we can then recover and learn from it. That's a very, very slow process, 10 bits per second. That's all that we can do as humans. Even so that you get megabits per second input through your eyes. How the brain processes that information ultimately to the point where you're able to be able to tell somebody else, you can retrieve the information and you can tell it to somebody else. That process is very, very slow. And so that basically says that we are very, very good at looking at titles or abstracts, but it takes us a long time to read a paper or look at a video or watch a movie. And that's sort of the open question here in terms of how can we go sort of one step further and tie this self-similar scaling of internet traffic to this basic limitation that we as humans have. And as long as we as humans are still the main users of the internet, we will most likely have this property there. Similar question you can ask with respect to the spatial allocation, aren't there future changes that you can imagine where things will make it very different? Certainly, if you think about these developments in terms of named data networks, this will make a very big difference as far as IP addresses is concerned. And then, another question is, why is it important for to optimize for scalability of IP address allocations? You can ask this question in view of, is this still important for IPv6? Because you have now such a much larger IP space that maybe other aspects become more important than scalability and stability. So there are lots of sort of questions that you can start asking now based on this understanding of this empirical phenomena like self-similar scaling, multifactor scaling, potentially other empirical phenomena that we observe in the future about internet itself or internet traffic. And this is sort of a blueprint of how you go about taking a phenomena and trying it, figure out, is there an underlying principle that causes this automatically, and it's not just an artifact. These are just two examples that we have sort of now more or less worked out. There is still future work to be done, but it provides, as I said, a blueprint for how to go more beyond just statistical analysis and mathematical modeling. Thank you.
Hi, thank you for the talk, Walter. So it seems like there is this recurrent theme in the talk that essentially we are observing behavior, but what we care about are the underlying causes. And a lot of those causes are actually the effect of human constraint. So shouldn't we try to measure those human constraints to begin with? Like, we don't really have a great grammar to understand these. What you've done for example, the spatial component is you looked at RN document to infer that these were the constraint and that resulted in that behavior. There happens to be, fields of anthropology and sociology that are looking into why those constraints arise. So do you think that this is kind of the direction that keeps us relevant in a way?
Well, I mean, so that goes into this direction of So, there is work on the sort of in the biology area, human cognition area, where they sort of end up with these experiments that demonstrate that we as humans have this enormous limitation in terms of processing information. And that limits everything that we do. And now you can ask the question, if the internet of the future is not geared towards humans anymore, but geared towards machines or whatever, as these limitations will go away, because data processing of machines are just orders of magnitude larger. So this is one way to sort of move further along these lines and sort of say, okay, do these experiments with how the human brain works, and ultimately it goes back to, what can you say? What do we know about the human brain, how it works? And we know very little about it. That's right now the basic. This work about the 10 bits per second limitations of data processing is just 1 or 2 years old. So these limitations sort of now pop up in that sense, but at the same time they also sort of suggest now this future internet scenarios where maybe the humans are not anymore the main consumers. That changes things.
So I was also curious, I mean, judging by the length of the prefix, you were looking at IPv4. And I'm just curious, have you looked at IPv6 and does that change the conclusion?
Yeah. So far we don't see any changes. The only thing that we see is it's just the IPv6 space is pretty empty. That's
It's still clustered in these.
But the way it's currently allocated still follows that policy that people took over from IPv6 or from IPv4. So that's still currently reflected. But what I'm trying to point out is, as maybe these registrars realize that there is this really big space out there where we don't have to worry too much, at least right now, about contention, about there will be enough resources available for the near future for sure. Maybe other aspects of optimization comes along, and I don't know. But right now we still see the same thing in IPv6 that we saw in IPv4.
So thanks again. Let's thank all the speakers. Thank you for coming and giving us the live portion. And again, thank you. We have people coming from out of state and the northern reaches of Manhattan. So we're grateful that everybody made the trip down here. I think we're due for a coffee break now. And then when we pick up, if we can get Mike Shapiro's recording, he did it live. It should now be recorded. We should be able to play it back. It'll be his keynote on analog computing, which I thought would be cool. But if lots of people complain during the coffee break, I don't want to learn about analog computing, we could skip it. But I thought it would be interesting. So go have some coffee and snacks.
Colleague in the Hebrew University, we are actually our office is sharing. We are sharing a wall, but fun fact: both of us went on sabbatical 2.5 years ago. He went to Cambridge, UK, and learned about analog computing, which we will hear about. I went to Princeton, and let's hear Michael out from London.
People online, do they hear us?
Yes.
Let's do the same thing again because this one. on, you can move on.
Oh, we are not watching.
Oh, perfect. Hi, everyone. Can you hear me? Okay, cool. So thank you very much for inviting me. This has been a pleasure already. And I wanted to tell you a bit about my recent adventures in analog computing. And I should start by acknowledging that these were made possible because of this team at Microsoft Research in Cambridge, a very interdisciplinary team that's working on a very ambitious project, namely building an analog optical computer. And specifically, everything I'm going to talk about is based on close collaboration with these guys, Christos, Kirill, Buju, and Hitesh. And basically what the analog optical computer project is trying to do, and there's people from Microsoft Research here, so I'm going to delegate the harder questions to them. Be prepared, Paolo. And but basically, they're trying to build a new type of computational artifact, one based on a combination of analog optics and analog electronics, with the hope of achieving orders of magnitude improvement in terms of energy efficiency and speed. And just before diving into the specifics, I wanted to say that Marwan talked earlier about the two buckets that problems we work on fall into. So there's problems that are motivated by pressing need or by big money or by external pressure. And then there's things that are beautiful to think about, right? So from my perspective, at least, this is definitely in the second bucket. I'm not saying anything about the real world impact, but I'm saying that what drew me to this project, which is something, again, that was is done by Microsoft, was that it's truly high risk, high gain, right? It's very early to tell what will come out of it, but I think that we already know that there's something very conceptually fascinating about this thing. And there's potential, and there's a lot of open questions. A lot of them relate to actually building these things, which is physics and low-level hardware, and I certainly am not the man to solve any of these, but a lot of them are very abstract computer science questions, right? We don't often get the opportunity to look at a new computational artifact and ask, what can it do, right? What is it good for? And maybe on a more personal level, it also made me realize how fortunate I am, maybe we are, right? And to appreciate academic freedom, right? The fact that I have time to apply things I don't understand to things I don't understand, right? Analog hardware to problems in real world control, and the world is silent, right? I think that's wonderful, right? So just a brief recap on analog computing. So what is an analog computer? It's basically a physical system, right? Where we're used to data, digital data being represented digitally as binary variables, right? Whereas in analog computing, it's represented through continuous physical quantities. This might be liquid pressure, it might be voltage, it might be light intensity. And the computation is basically just letting physics do its thing, right? So we configure a physical system in a certain way, and then we let the physical dynamics of the system evolve towards a solution, right? Maybe we don't often think of it as such, but a thermometer, right, is a very simple analog computer, right? There's external temperature, there's the physics of the mercury moving around, and it computes some continuous quantity, which in our case is the measurement of the temperature. And in addition, it's the original form of computing, right? There's evidence of analog computers tracking the movement of celestial bodies in ancient Greece 2,000 years ago. But it's not just ancient history, but before modern computing, during the 40s and 50s and even 60s, right? This was the prevalent form of computing. And it had a lot of applications for process control, for bomb site control. differential analyzers like what we see in this picture. And by the way, I neglected to mention, but this is a conversation, so please, if you have any questions, don't hesitate. But we all know that this is a story with a sad ending, right? Because ultimately, analog computing, I don't know if it's a sad ending, but for the purpose of the slide, right, it's a sad ending. Ultimately, analog computers were replaced by digital computers, and rightly so, right? Because they have better precision, they're much more scalable, and it's all-purpose computing, right? They're programmable. An interesting thing, though, is that in recent years, we've seen a surge of renewed activity in this domain, both across corporates and across startups. And it's not hard to guess why. It's because of what's driving all activity, right? In the hardware space, or a lot of activity in the hardware space, which is the exponential rise in computational demands. And this is what we're seeing when it comes to unconventional hardware in the form of quantum computing, like quantum simulated annealers. And this is what we're also seeing when it comes to analog computing. And there's a catch, of course, and the catch is everything I said in the previous slide, right? There's a good reason why these things were eventually replaced. And in particular, this is not all-purpose computing. So for analog computers to succeed, we have to identify killer apps. And these killer apps are going to be certain types of computation that are amenable to this kind of computing and that are important enough, right, for people to actually pursue. And in designing analog computing solutions, we're going to have to also deal with the things that made them obsolete to begin with, right? To address scale, to address precision, to address programmability, right? Maybe within a more confined space, right? But we have to address them. So the way I think we should think about this is something Peter said to me once. The way I think we should think about this is really the way we think about hardware accelerators, right? That is, we are accelerating or we're improving the energy efficiency of specific types of operations. And the question is, which and why? And these are actually the two things that I've thought about the most during my interaction with folks at Microsoft. It's these two questions. What is the computational expressiveness of analog computing? So at an abstract level, what types of problems can we solve? And I would argue that we need to understand this abstractly to understand, right, what the limit of these things are and what falls within the boundaries of quantum computing. And the other one is where can they shine, right? Meaning not 10 years from now or 20 years from now if we address a lot of scalability challenges, but are there things that are happening now that could potentially benefit from changes and from analog computing? And as I said, I think these are important in the sense that the first question is one we need to answer if we want to guide next generation quantum computing and next generation analog computing and next generation analog algorithms, right? That is how, if we want to push the state of the art forward, in which direction do we need to do it? Yes.
Did you select order these two questions? And the reason I ask you we really want to know where it shines before we think about the expressiveness, the hardware, and the algorithm. So I actually like that you selected it this way. Peculiar and somehow.
Firstly, thanks. And secondly, historically speaking, I don't know that I have, but I think I may have, because for me to figure out where it might be useful, I needed to somehow phrase to myself where it might be applicable first, right? I mean, I would love it to be useful for LLMs, right? But if I don't have an abstract understanding of the limitations, right, then maybe I'm missing on something. So I think that's probably the underlying reason for that specific order. But as I'll show later in the talk, these questions happen to be very closely related, even in terms of the answer. So I think we can show that. Let me get to that when I talk a bit about what I think might be first steps towards these answers. So regarding the second one, though, exactly what you said, right? What are we doing this for? I mean, by the way, the first question in itself is, I think, intellectually fascinating, right? But it would be nice, right, to also have some kind of North Star, right, to guide this. So I want to ground this discussion, and a lot of this talk is going to be grounded in Microsoft-specific hardware, right? But I do want to step back and say that I think that there's general principles here, and that you could do the same type of analysis and the same type of a theoretical spiel in other contexts, right? So when Microsoft introduced their AOC, their analog optical computer, they also introduced this class of optimization problems that I will use to, again, make this discussion more concrete. And then the title is very indicative of what these are. That's a good thing about the title. It's quadratic minimization that's unconstrained. There's no constraints, right? And that's mixed in the sense that variables can be both continuous and binary. Okay, and the reason that they've introduced this specific class of problems is both because it's an extension of another specific class of problems that were coined in the context of quantum annealing. So that was a broader class, but also because it pretty much exactly captures the strength of the hardware in terms of from an optimization perspective. And I will note, because later this might make an appearance, that you can incorporate linear constraints as penalties into the objective, right? Later on, you might be curious about how I hand wave my way around linear constraints, so it's right here. And to address this and other types of problems, Microsoft introduced AOC, right? Where AOC is not that big. This is the second generation of AOC, and it was specifically designed to fit inside a rack. Right? And now, here's how it works, and this is still mind-blowing to me. And I feel free to say this because I have nothing to do with any of this, right? This is just the way that AOC works, but it's sort of like watching a magic trick. Sort of, you have a vector, these are your variables, where the values are represented as light intensities. And then what you do is you take you take these light intensities, you take this light and you project it onto a matrix of programmable filters. And what happens is you can sort of think of it as multiplying the values of the vector by constants. This is what's really going on. And then, so this was a fan-in step. Sorry, the opposite. This was a fan-out step. And then there's a fan-in step. Right? So we're fanning out across the row, then we're fanning in across the column. Can you guess what this is? What mathematical operation looks exactly like this? Matrix vector product. Right? Cool, right? So this is a very well-known trick from optical computing, right? But it's nice to see it at work. And basically what's going on here is that you can multiply, right, a given matrix, W, think of this as fixed, right, by variables, by a vector of variables. And then the next thing you can do is this was all in the optical domain. You can use analog electronics to apply nonlinearity to the specific coordinates. Why is this useful? Firstly, because some of these we see, for example, in applications in machine learning, right? But even a simpler answer is, if we want to emulate discreteness in a continuous world, these are good ways of approximating it, right? I might not be able to project on 0, 1 exactly, but I can sort of make the variables closely approximate a binary assignment. And the cool thing is that this goes on and on in the analog domain until we decide to stop and look at the result, right? So basically, what is it that we've done here? Gradient descent, right? Because the gradient of a quadratic problem is a matrix vector product, right? So this is gradient descent at the speed of light. And at some point, you can measure and see what the answer is. Yes?
The lines, they are final, right? Like this.
Yes, yes.
The analog electronics need domain to each.
Exactly, yes. So there's photodetectors here, right? There's a transition to the electronic domain, right? And then a transition back. But this is not digital to analog, right? These are transitions within the analog. That's right.
Is that some sort of bottleneck doing the domain every time?
That is a good question. And I am told that not so much, but I won't defend it, right? Paolo, you want to defend it?
You don't even need to digitize this, but you can keep in the analog domain. This is where things can be really efficient. And this is different because there have been other approaches looking at optical compute, but where they were all falling short is that every time you need to go back to the digital domain and you need ADC and DAC, suddenly you have a massive hit in power, and then to some extent you were losing all the benefit coming from this. But if you can crack this OEO conversion in a cheap way, this may have a good chance.
So keep this in mind, right? What we're doing is we're doing a gradient step, right? In the analog domain, in the analog domain. And actually, when you look at the actual algorithm running here, it has more components because we don't want to get stuck at local minima, right? There's momentum, there's simulated annealing. You might start at multiple different places. But I think the takeaway is you can explore extremely quickly. And because you can explore extremely quickly, you have hope of reaching a global optimum, even where digital systems might fail. Yes? Okay, yeah. So let me get to this. No. So this is the picture, right? but it's scaled larger. That's the next thing. I have a slide for that. Okay. So, but following up on what Paolo said, one of the key points that Microsoft was emphasizing was using consumer sector technologies, things that we have in projectors, things that we have on our phones, things that we have in like micro LEDs, right, to make this thing happen. And going back to your question, we are here, right? And you can see the number of weights, but from our perspective, you should really take the square root of what you're seeing there, because when they talk about weights, they talk about the matrix, right? But the size of the vector is what you'd care about in this context, right? But as you can tell, right, this is impressive, and these are problems with thousands of variables, right? Actually, Francesca, who's one of the leading figures in this project, at some point, this is generation 3 that they're working on. At some point, she gave me a present, which was this model of the next generation of AOC. And the mind-blowing thing was that it was to scale. So it was literally this big. You have these micro LEDs sending across the. So going back to our two questions, here are the best answers I came up with so far. One is trying to abstract away from the analog device and trying to characterize the types of problems that it can solve and trying to push the boundaries a bit from the current hardware. And the other is real-time control. And going back to your question, Marwan, the interesting thing is that the two are, there's a lot of synergy between the two. And I will try to do that in this talk, actually, to explain why you need more expressiveness if you want to address more sophisticated problems in real-time control, and the opposite, to motivate the hierarchy through real-time control in different applications. Yes? About, yeah. So, I'm sorry? Yes, so I was asked about the accuracy of the result, and what was shown in that Nature paper is that they get remarkably high accuracy compared to what you'd expect. And one thing I should say about the process itself is that it sort of addresses a lot of I think it implicitly, because of the hardware algorithm co-design, it addresses a lot of the known limitations of analog computing. So, for example, the fact that gradient descent is very robust to asynchrony, right? So I think the algorithm was sort of tailored to that context, right? As long as there is some descent direction, right? Don't necessarily have to optimize for it. And then there's the question of, reading out the outcome, where measurement errors might occur, but they show empirically that they get good results. Yes. Yes. You are me 2 years ago. 2.0.
Maybe it will take me a little bit longer for me to catch up. But I was wondering, does this have any advantages when it comes to our environment introducing errors to these computations? Because in the digital domain, we have lots of error correction. We were earlier talking about sending things out to space and how bad it is because of bit flips. What happens here?
That's a very good question. I will try to address it in this talk through two different things that I will get to. One is the scale. It's a different scale, right? So when Mark was talking about the huge scales, right? An error is a fact of life. Multiple errors are a fact of life, right? So here we're talking about very different scales. Also, not exactly the bit errors that you mentioned, but say perturbations to the input, this actually can help with. I'll try to linger on that. So what is the expressive power of analog computing? There's two very vaguely defined terms here. One is what's analog computing, the other is what's expressive power, right? So when I talk about analog computing, there's two possible characterizations. One is single pass feed-forward operators. There's been work on optical neural networks. I'm not talking about that at all in this talk. The other are systems like AOC, right, that try to exist in the analog domain and do a lot of fully analog iterations, where the idea is to avoid the costly analog to digital conversions, right? Basically, it happens twice: when you formulate the instance for the analog computer to solve and when you turn it back into digital, right? And there's a lot of examples other than AOC that you can categorize inside this class. Now, what's expressive power? That's a harder question, actually. And I'm going to hand wave around it, but I will say that, and I think you will see this when we talk about what types of problems we solve, that we will basically be reverse engineering from the hardware primitives, right? Trying to ask what puzzles can we construct using the same hardware primitives. So what is it that we've just seen? Let's step away from AOC, right? We actually saw fixed point iterations, right? So what AOC did was it applied a linear mapping by multiplying by a matrix. Then it applied the nonlinear mapping in it must have this form, right? It must be such that you're stuck. Why are you stuck? Because applying the linear mapping and the nonlinear mapping puts you back in the same place. And AOC is just an instantiation of a generic solver, right? For this problem, which is just continue these fixed point iterations until hopefully eventually you stop. What could this F be? So we have a matrix W and the nonlinear function. It could be, for example, the gradient update step. It could be neural layer activations. It varies across applications, but this is basically the abstraction. Yes.
For example, the analog step. So, not to detract from the abstraction, but
yes,
in a practical, like an implementation, presumably the perturbation step, the analog step, could take you 2 iterations away from the solution, in which case that would not be true. Like, how does that happen? Do we worry about that? Does it?
I think, well, for sure we worry about non-converging, right? As we do with any gradient descent process, any fixed point iteration process. Another gradient step won't take you further. I won't go deeply into this. I'll touch on it later. There's also various types of neural networks, right, that sort of smoothly fit into this framework. So what I'm going to do in the remainder of this talk is I'm going to walk you through this set of abstractions, and I'm going to do this through the story of real-time control. And the reason I'm doing this is because I think real-time control is interesting in itself and can benefit from these abstractions. So we are starting out here, right, with model predictive control. How many of you know what model predictive control is? Okay, the rest of you are in for a world of excitement. Okay, so I will talk about that in a bit, but then I will show you how I think with the advent of analog computing, we might actually be able to perform more sophisticated vehicle control strategies that are today limited by the online speed. So I should say, as a networking person, the most exciting thing of graphics I show is a CDF of something, right? So this is, I've always envied the computer graphics people, and this is it doesn't actually compete with them, but it's a it's a big step for me. So show your appreciation. And so what is model predictive control? So let's look at a simple example. We have 2 dots, the white dot and the green dot. This is a 2-dimensional plane. The white dot is us. The green dot is moving according to some fixed trajectory, right? What do we want to do? We want to closely track the green dot. How do we do it? Our actions are exerting forces on the white dot. So we can exert a force on the x-axis and on the y-axis. And there's a physical model of the system that says if you exert this much force here and this much force in that direction, this is where the dot will be next, right? And so this is basically a very simple control task. And I will illustrate everything through extremely simple control tasks. And the way we're going to do this is model predictive control. Model predictive control is the go-to strategy in control theory for when you're handling a sophisticated sequential decision-making problem, right? But it's actually remarkably simple intuitively. It's just look at the current environment state. In this case, it might be where I am, right? My velocity, right? And then look at a bounded time horizon. Maybe I make a decision every 1 millisecond, and so I look 10 milliseconds into the future. I have an explicit physical model of the environment, so I can actually optimize for the best sequence of actions. So I'm trying to actually optimize and find my next trajectory of 10 actions to be the best based on some cost model that I have. Once I do that, I apply the next action, which was the first action in my computation. I see what happens, and then I repeat this process. Right? So basically, all I'm doing is I'm looking ahead into the future. I know everything about the world, right? This is why this is for a very specific class of problems, right? Where robotic arms, factories, et cetera, where you actually have an explicit model of the world. I optimize, and then I take the first action and re-optimize. And model predictive control is very much a real world thing, right? So I don't know if you've seen the Boston Dynamics robot backflipping. It's solving model predictive control online. Isn't that amazing? So fundamental to the theory of and practice of real-time control, a lot of real-world applications. And I would argue that all the stars are aligned for analog computing here. Why is that? Because there's frequent and very intensive online computation, right? That's the first requirement. We have to care about computing time. There's a natural combination of continuous and discrete variables. I was talking to this robotics guy, and he said that when humans are, lifting a cup, they're implicitly deciding on how many fingers, right, to use. Or think of process control, where some of the machines can be switched on or off, right? So some of the variables, temperature, for instance, are continuous, others are discrete. Non-convex objectives, what people do in practice is they massage the objectives to become convex, but obviously, right, they might miss out on important details. And maybe most importantly, or second most importantly, it's very compatible with the formulation of problems we can solve even with existing analog hardware. Whereas if you look at a control theoretic book, what you would see is quadratic optimization with linear constraints when they discuss model predictive control, right? So it's all, we don't have to actually tweak the problem to make it fit. And lastly, the scales, right? That is, again, I don't know if we'll ever see analog LLMs or even analog ML models that are orders of magnitude smaller, but here, thousands of variables is a lot, right? These online problems, right? You have state, you're looking into the future, you have your actions, but thousands of variables for a 1 millisecond operation is a lot. So just to give you some intuition, if you look at our specific example with the white dot and the green dot, what would it look like mathematically? You have some cost function. The cost function is there's a bounded time horizon, capital T, and you are trying to stay close to the green point. S is the state. I want to, my state, think of my location, to be close to that of the green point. And I also want to minimize, U is the control action. I want to minimize the control. Right? I don't want to exert a lot of force. Right? This is a very standard cost objective. Are you with me or just dazzled? Okay, okay, thank you. That was very kind. Not true, but kind. Thank you. And in addition, we have a linear approximation of the system dynamics. So what my student did at an internship at Microsoft Research is he actually implemented a prototype for analog MPC. And what that involved was basically taking the simulator of the analog optical computer and having it interface with Mujoko. Mujoko is one of the canonical, maybe the canonical platform for evaluating control tasks in simulation. If you look at a lot of robotic papers, they actually have experiments in that framework. And what you just saw actually was that, right? The simple control task implemented in Mujoko with an AOC simulation in the background. And we try to identify tasks for which analog control is natural. And I want to say that there's two possible ways to win here. One is to be faster than existing solvers, but the other one is to have a better policy. Why would you be able to make better decisions? Because maybe you can solve for a longer time horizon, right, at the same time frame. right? Maybe I could just look ahead more, and I will know that I shouldn't move in that direction because there's a wall ahead, right? Whereas someone that optimizes in a more myopic way will take one step after the other until that wall is right in front of it. So I will give you two very simple examples, but I think they're cute. One is discrete actions. So on the top, you see the analog MPC planner. Here you see a gradient descent planner. That's an MPC planner implemented into Mujoko. It's myopic. That's what you should remember about it, but it's also continuous. So how does it actually work? It optimizes something continuous, and then it binarizes after the fact, right? In contrast, what the AOC planner is going to do is it's going to optimize while making the variables discrete. And this is the consequence, right? So what you see here, it's actually solving the right continuous problem, but then this binarization after the fact leads to so there are different forms of dancing, right, of the white and the green dot. But this is obviously a better policy in terms of the cost function that we're optimizing for, because you're almost on the green dot all the time. Now, here's a more interesting example that I think reflects why you might need the speed and computational power of analog. Here's a very simple example. We define this class of problems that we call track and avoid. So far, we wanted to be close to the green point. But what if we also want to be far from the red point? Right? There's a risky area. There's an area with high wind, right? So now, what would my cost function look like? Maybe something like this, right? Ideally, I would be on the other end of the green point and far from the red point. But as I get closer and closer to the red point, I suffer increasingly, right? And for the suffering to end, I need to do something very non-myopic, right? I have to get through it, suffering more and more in the process until eventually things get better, right? And all of these myopic MPC planners are going to get stuck here, basically. Whereas if you were to optimize globally, you could arrive at the correct point. And let me show you a very simple 2D example. I think it's actually cute, where this is a 2D version of what we've just seen. I want to be here. I don't want to be close to this guy, right? And I'm that white dot. So the optimal policy here is counterintuitive. It's going through the red dot, right? And going all the way to the end, because I'm going to stay there and benefit from that in the long term. What you see at the top is this effectively happening in a very non-convex landscape. What you see at the bottom is convergence to the local equilibrium, right? Where basically I'm further away from the red dot. I can't get any further because that's the boundary, right? And I won't get any closer also. So basically, what have we learned from this? We've learned that model predictive control very naturally fits in this fixed point optimization framework. And if we extend this framework, suddenly we have more possibilities, right? Possibilities that today are fairly far-fetched to do online. So, and I will talk about two of these, robust MPC and MPC with learned world models. So going back to our simple example, let's imagine that there's also an adversary that's slightly pushing us, right? So we make decisions, we exert force, and there's some devil, right, that slightly nudges us in different directions. So this is a minimax problem. I am trying to minimize the cost, but there's someone working against me. There's someone who controls part of the variables and is trying to maximize, right? In this case, he controls what's known as the disturbances. The disturbances are shifts to my model, right? Like, why does that make sense? Not because I'm actually concerned of an adversary in the 2D board, but because it's a very good way to model inaccuracies in the model, for example, right? Or things I couldn't model for. Right? So I don't fully trust the model to be perfect, right? I may want to be robust in the sense that I perform well even for adversarial perturbations within a certain region. Yeah. So it is important, and this is robust MPC in the control theory literature. There's many manifestations of it. This is a sort of minimax manifestation, but it is important because eventually all of these things need to be sucked into the objective function. Right? The problem is unconstrained. So there are some structural properties that you need. Luckily for us, this is very faithful to the way things are modeled in robust MPC, but that also explains why some things are impossible. Right? You may not get something quadratic if you start absorbing these terms. Right? So in general, minimax optimization is a very broad class of problems, right? Where again, someone holds part of the decision vector, someone else holds another part of the decision vector, and they have conflicting goals. Or in more vividly, someone is trying to harm the other. And what is this useful? Because these problems arise all the time, right? I want to optimize the performance subject to failure scenarios, subject to unanticipated user demands, right? Or in our case, subject to adversarial modeling errors. And you can capture these things by thinking about the problems we've looked at so far and turning them into minimax problems. And let me now sort of give you intuition for why this is helpful, because what's a very standard approach for solving such problems? It's just an extension of gradient descent. It's called gradient descent ascent, where I improve my variables and you improve your variables, right? For me, that means minimizing. For you, that means maximizing, right? This can basically be implemented using almost the exact same machinery we've been using so far, right? There's a lot of literature in game theory and optimization from which we can borrow ideas to make convergence better, right? But the point is, all of the core elements are there. Yes?
AOC, we would need to express more traditional systems optimizations problems.
So when you say more traditional systems,
I'm thinking of some global scheduling policy that you want to apply on a machine, or a distributed system.
So I think if you look at the like projected hardware efforts, the numbers that they mention are in the orders of thousands of or tens of thousands of variables that they want to reach in the next generation. So this is why when I was searching for problems that might be appealing, real-time control was appealing to me.
Mm-hmm.
But if your problem has 200,000 variables, that means you will have to wait, right, for the analog hardware to catch up.
All right. I was just wondering if there's a realistic system scale that would where an existing AOC would fit.
So I think that for these problems, right? If you talk about, again, we've talked to practitioners doing process control in various contexts or doing robotics, and for these problems, at least on paper, the next generation of AOC could be applicable, right? That these are the scales, right? Once you go beyond that, you need to check that you can actually represent that. So I don't want to linger on this for too long, but we can, but basically this is an instance of a broader class of problems where you have two players. You have two players and they're working against each other. And just to give you a taste of what this could accomplish, so you've seen one, right? One is robust MPC. I'm trying to optimize my control strategy, but I want to be robust to perturbations in the model. But the other one that I think is super interesting, and this has recently been popularized by Jan LeCun, right, who objects to everything LLM and is in love with MPC with learned world models. But basically, this is of course a very different context. But one of the things that you can show actually can fit in this framework is, so far we've been talking about linear models. That is very common because people actually typically do linearize the model because they want to be able to solve simple online problems. But it has two problems. One is that linear models can be inaccurate, and they're more inaccurate the further away you look, right? The longer the look ahead horizon. The other is that linearization happens digitally, right? So you still spend time linearizing the model. What if instead you had an analog model, an ML model that was implemented in the analog domain? Doesn't have to be extremely big. It just needs to be more expressive than a linear model. And that you could actually just stay in the analog domain throughout and use. Right? So this is one other thing you can implement in this more abstract framework. And there's more things, right? There's more things. We can generalize this to multiple player games. All of these abstractions, pretty much all of these ideas extend. I'll just give you intuition for why this might be important. If you think of cars at an intersection, if you think of multiple robots in a shared space, it's not just me optimizing my trajectory. I also need to sort of anticipate what you're going to do. Right? So even if I'm only optimizing for myself, I need to know that if I accelerate my speed, you're not just going to continue at your current speed. Right? And that there's several recent work showing how this boils down to computing an equilibrium over a finite time horizon. Once again, very amenable to the exact same hardware primitives. So bottom line, this is an abstract perspective on the power of analog computing. I think that there's a lot of interesting research questions there, both in terms of extending the hardware and in terms of identifying the killer apps within and without real-time control. And that's it. Thank you very much.
Hey. Oh.
Yes.
We will hear the question. Because you cannot ask right or not next time.
Well, if you can text them, what does this have to do with networking?
Yeah, that's the first question. And then he said, "Oh, I'm going on a flight now." So
I think they killed the mic. Anyone care to comment?
Yeah, so it's not a networking talk, obviously, although but
I mean,
his thoughts.
Just a general question is, I mean, I felt like the keynotes, most of them were not networking in a traditional sense. And I think that's hints at the fact that networking as a whole is evolving. And maybe it's an outrageous opinion, but what even is networking? Like, what are we doing?
Like quantum computing, and now we have quantum networking. So maybe some stuff will come out of it eventually, but certainly this one is like a control kind of.
So just speaking of Mobicom as a conference, the underlying math that goes into some of the analog computes and how the actual addition happens has some parallels to massive MIMO. So if you actually think about being able to control signals and using the medium as an additive mechanism, effectively a similar type of math happens. Not exactly the same, but here you're actually having control over the source, control over the intermediary, and you're able to repeat this in a certain manner, but over there between the sender and the receiver. If you're thinking about this in constrained setup where you have control over both the source and the receiving and the intermediary medium, the math starts to overlap. So given that Mobicom has actually gone into a lot of like very low layer wireless as a networking field, if you think about 10 years from now, where potentially there may be more robots than humans, and if you're thinking about robots interacting with each other and such kind of miniaturized devices coming within a robot, you might suddenly see a huge wave of analog computes within robots for that real-time control, which gives you that sort of MPC with the localized control with the corresponding world model, and these robots interacting with over traditional protocols. So you might actually see like a very interesting wave of a different spin on it coming, and networking starting to play a big role in the space. So I just wanted to.
So my understanding of MIMO is, I mean, you're operating in an analog space, but they're not trying to utilize the analog properties to solve any problems or transmit information, right? It's just a matter of separating the signals such that each signal can be clearly transmitting digital information as of now, right? There's no attempt to transmit analog information.
So just to draw a parallel, 24 years ago, right? There was a faculty candidate talk at Berkeley by Michael Gasper, who was talking about analog communication and being able to squeeze the juice. And I was talking to my advisor, Scott, saying, why don't we use this in a way to actually do analog specifications and analog? And he thought it was a really foolish idea for what it's worth. And then, fast forward 4 years later, Sachin and Shyam exactly used a similar insight to start doing analog computations on the fly to maximize the capacity. And there were certain parallels that came out of it that then led to significant advances on massive MIMO in certain fronts. And just sort of, if I had to do a parallel between that line of thought to this line of thought, my speculation is something like this could end up in certain miniaturized environments like a robot and could start to make a wave. Now, the real question for me would be, where does this kind of compute actually make sense and where does it not make sense? So if you had that extra few milliseconds to just convert to digital, do massive parallelism and do everything, it's quite possible that we might be in certain scenarios where this actually doesn't make any sense. So I really liked the very first 5 minutes of his talk where he said, I do not know where it's going to be useful, but here are specific scenarios where it's actually potent. So I think miniaturized robotics is a great use case, the way I see it in the short term. So
I think robotics, but also maybe load balancing or congestion control where you don't need precise answers, but you need to converge to something, that sending analog signals instead of digital and trying to, read off those might be also a useful paradigm. Anyway, food for thought and thought for food. It's lunch. So any other comments before we go? Okay, we'll reconvene in like an hour and we'll do the research outrageous opinion session. So think of ideas. Hopefully you've been inspired by analog computing. If you didn't have any wacky ideas before, now's your chance. Think it over lunch. And if you found watching a presentation like that boring, please be more participatory, or we are going to just watch videos for the rest of the afternoon. So to have good ideas, well, some people only have good ideas, but I'm not one of them. I have lots of crazy, stupid ideas, and I work closely with Vishal Mishra, and he once told me maybe 1 out of 100 of your ideas is a good idea. So just to set the context, if you have an idea, the best thing you can do is tell it to other people and see what they think. I don't want to be up here the next half hour just talking about my crazy ideas. So I'm hoping other people will feel free to speak about whatever it is they want. And if not enough people, or just describe the research you're working on, even if it's not a crazy idea. That's also what this session is about. So feel free to come up and talk about what you're working on, and or just an idea you have that may be crazy or not. And if people don't come up, I will just start spouting stuff off. And I don't think it'll be as exciting. So does anybody want to be the first volunteer to come up with, describe what you're currently working on in research, or what people should be working on, or what they should not be working on, or previous talks? Good ideas, bad ideas. I mean, really, we should be discussing these things and not just taking everything said as ground truth. We should always be questioning stuff. So does anybody want to start? Volkman?
Thanks, Dan. Just to give a bit of context, Dan knows I have crazy idea because he's my advisor, so he has seen some of those crazy idea. I think one thing that is becoming apparent is that there is a lot of networking problems that exist in very different environment, and that the community as a whole has focused on specific, like a lot of the research is now on data center and so forth, but there are, for example, part of the world where people don't have access to fiber or don't have access to any kind of reliable connectivity, and that these kind of problems should also matter in our community. And I'm just kind of curious how we can make sure that when we're doing networking research, we also acknowledge this environment and we don't only develop solutions that are applicable for like a very small part of the iceberg. I don't know if it's a controversial idea, but it is an idea, something to start to think about.
Anybody care to comment?
Yeah, the tip of the iceberg. Like a lot of the problem we're tackling are the tip of the iceberg for users. Like this problem exists for this specific company, but there are other problems that exist for billions of users that are considered less researchy because there might be already a solution out there to address them. The bottom line is it isn't addressed. So, kind of switch the framing of what constitutes a contribution in a way is my hot idea. Like developing a system for a remote area of Indonesia might not appear as a contribution at this point, but if you address a real problem and you actually help connectivity in that specific region, that could be considered a contribution. So that's my hot take.
I was just going to ask, maybe frame this a little bit differently. Have you thought about questions or, some papers may have a really interesting idea, but people would ask, okay, what is a hot workload? Either machine learning, which is, most of the cases these days, they will ask, okay, what is an interesting workload that might warrant this sort of contraption that you are doing, or whatever complicated or fancy stuff that you're doing? I wonder, what is your take on that front?
I think the talk from Michael was kind of arguing for the point that there's like kind of two sets of research. There are two kind of research, right? Like there is this far-fetched, this might not be realistic now, but I still think it's worthy of investing time on it. And then there is the more like, right now there is this problem and I'm trying to tackle this. That's my my hunch is that sometimes you don't really have workload, but if there is a scientific contribution, there's like advancement in the way we think about problems, still warrants to be published, still has value to be out there. And so we should kind of value both. And right now, sometimes we tend to maybe bias more toward one direction, but that's my 2 cents on this.
Well, so I have a flip answer to your question about how to maybe change this direction, and that would be you introduce non-experience paper sessions in SICOM. So right now we have experience paper sessions. And if you look at the experience paper sessions, they are dominated by the hypergiants. They talk about experience that nobody can check. Is this research? I don't know. So you could imagine something opposite, something very, it's just sort of the opposite of experience papers that invites stuff that is more open-ended, looks at questions that are not geared towards industry. But would you get any submissions in that space? Would be a question.
Of the idea.
I'll just add that I think back in the day, there was less money in networking, and when money poured into networking, people's focus tended to go toward where the money was. And so there have been some papers or some folks that have looked at that, like Ranveer Chandra at Microsoft. I remember he was very interested in these. And I think Lakshmi also went through a period where he was not here, but he was looking at, oh, there you are. Weren't you looking at networks for low income? Yeah. So, I mean,
So, I don't know. Okay, so there's a conference called ACM Campus, Computing and Sustainable Societies. And I want to just share a story. Back in 2009, when we wrote a SICOM paper and we got back a review saying, why don't these countries get better connectivity? And we said, why don't you go live there? It was actually a turning point in my career where I decided not to submit to SICOM for a very long time. And we basically started our own conference called ACM Dev, Computing for Development, which became ACM Campus, Computing for Sustainable Societies. And I'm happy to say right now, and I don't know about Columbia, but outside of maybe Columbia, in the top 20 schools, everybody has hired at least one faculty member doing computing for sustainability as a primary thing. And now we even got Priya Danti, who was recruited at MIT. So there's like a massive wave of people looking at sustainability problems at scale and actually solving them and getting tenure through this whole process. And the journey that I was involved in, where we were doing long distance Wi-Fi connectivity and so on, led to a company that some of the students launched called Tarana Wireless. And now Tarana, I'm happy to say, is maybe close to $10 billion worth of, it's actually the leading backhaul provider for pretty much every cellular company in the United States. And it's actually working for rural connectivity with US government and FCC, and is actually doing also connectivity solutions in Africa and so on at a fairly massive scale. So that journey that I was involved in, after I stopped writing papers on it, that journey actually continued through the eyes of Tarana Wireless. So it was a pretty big journey. And they struggled a lot during the early phases to figure out what is the product market fit, how do you actually make money, and how do you actually do both social good as well as, so talking to Dan's point about the trail of money, it is not easy to do business in this space, right? Even right now, when I launch like social good relevant startups in some of these emerging markets, it's actually very hard to make money. And we tried to compete with Google for doing ad exchanges in Africa. And we failed, right? And I told Google that it's not working. And 4 years later, Google shut down its NBU unit, next billion users. Even today, Google and Facebook does not make money in many of the countries, including, I don't think they're cash flow positive in India. Right? They have massive resources put into a country like India. They're barely hitting cash flow neutral. So the trail of money does play a big role in how economics plays a big role in how these things actually work out. So a lot of people who are doing this kind of work, it actually became very hard to publish in SecCom and SDI because also the mentality was, yeah, this is kind of cool stuff, but I really don't know whether this is actually going to work through, right? Ehsan from Pakistan had a paper called Web Affordability Index, right? And that's among the very few papers that has appeared in SecCom in the last 10 years on this kind of topic, right? When I applied for tenure, my first sentence was computer science focuses on 2% of the world's problems. There is 98% of the people who are still out there struggling. So yeah, I have more negative stories to share than positive ones, but unfortunately, that's how academia operates.
I'll also just add that periodically there are like bursts of interest in certain topics that kind of come out of nowhere, a little bit surprising. Like delay tolerant networking, I would say, is something that nobody was thinking about. And then there was this paper that appeared, and then suddenly there was a whole line of work. And now it's the satellite stuff, right? I mean, I think we always knew you'd have these satellite networks. It just took a while for it to catch on and be feasible. There's always this trade-off between what can you do now and where are things going to be in 20 years. And the question is, the work you're doing, where do you want to sit? Being in academia, you've got the opportunity to reach further, but there's still always a pull to do stuff that's relevant now. And you have to kind of walk that line all the time. Anybody else?
I guess this is like a hope as much as anything. As I was driving here today, I was thinking about when I was a faculty working on internet censorship, and we had all these cool results. And PhD students, like, no one has time to write blog posts or anything. And I was sort of thinking, like, yes, LLMs, it's a 4-letter word at this point, but like the idea that maybe we could use LLMs and this to improve science communication, so more outreach. So it's not really a research thing. It's just it's a hope that, we can use this new technology to, like, especially when we have topics that are relevant, like censorship, policy. So I don't know, maybe instead of writing more papers, we can think more about, using this technology to generate text that is more accessible to people. I don't know. That's just my kind of thought of the day.
That's actually happening in a lot of underrepresented countries. The way education is transforming, it's actually quite amazing how they use some of these tools, especially the new video generation tools, to create positive content to actually teach new educational materials. So
we're interested in hearing from students. If anybody has an opinion on anything, you guys don't think about stuff, just do what you're told.
I was telling Dan that a few of us are continuously talking. We should stop talking and let others talk.
Yeah. Well, anybody get any inspiration from the analog computing talk? Anybody get any ideas? All right. Let me ask this. What would analog computing be good for in networking? All right. I claim it'll be good for congestion control.
So one thing that I think became apparent as part of Cyrus' talk is that congestion control in heterogeneous environment, very hard to kind of converge, and essentially it ultimately depends on what is your goal. So is the problem really the signal, or just the fact that you need to converge very fast on an agreed upon goal? analog really answering that part of the question of like, we need to find a way to have all the different actors who are sharing this bottleneck agree that this is what we're trying to get out of this connections.
Can I talk about something else, if possible?
Oh, any other takers? Oh, yeah, please.
Okay.
Step to the stage.
Yeah, all right. Hi, I'm Andy. I'm a second-year PhD student. I guess I introduced myself already. Yeah, I just want to bring people's attention to the fragility of our cyber infrastructure. So I don't know if you guys noticed, I think it was last October, we had a major, was it Azure and AWS outage. I remember I woke up in the morning, I couldn't get McDonald's because their whole thing is down. It's also trading on Robinhood. So also, yeah, McDonald's, Starbucks, can't order Starbucks, which sucks. Yeah, so it turns out the issue that took down the entire internet was because they had a race condition in their DNS agents. So apparently so they had a few agents checking like the DNS of the entire eastern US region. And they had an agent that, checks the current DNS plan and then would delete old plans, but then they never checked whether the delay between the check and the delete. So there was a congestion or something, and that caused the check to happen first and delays happen later. And that delete the entire DNS plan. So nobody gets DNS. So the whole thing is dead. And there are similar outages, right? That renders the entire system vulnerable. Like for instance, there's been an OpenAI outage where their control plane got overwhelmed, and nobody apparently discovered it for 20 minutes. That took out like ChatGPT for 48 hours. Yeah, I think there's the current research. Part of my research that I work on is called metastability. So this is another set of data center failure that's quite catastrophic. So what will happen is that let's say you have a data center that is quite overloaded, and you experience a shock. And what will happen is that the shock will render a data center at a very low performance, and it would not return even after that shock gets removed. There are many reasons for this. One of the reasons is that you get a retry storm inside yourself. So that shock has caused your internal data center to have, exponential work amplification that caused you to just doing useless work. And you have to manually restart the entire thing. I think one of the worst offenders had like 48 hours of outage of like entire Eastern US, parts of the entire internet. Yeah, so I think I just want to bring attention to the fragility of our infrastructure, and I think we need to look at those issues very seriously, because this can be very costly. For instance, like one of the outages that caused American Airlines service to go down, that is like $100 million an hour, which is kind of crazy. So yeah, so bring attention to this issues. We don't have many people working in those areas. Yeah, and these problems are very hard because it's really hard to see them in advance. So yeah.
How do you fix it? I mean, not necessarily the solution, but like, what are the approaches you would recommend?
Well, I recommend first at least identify those issues, right? Like for example, I give a talk at Hotnets identifying this set of problem called metastable failures that are, we're seeing a lot of patterns. We compiled a bunch of
public events, we see a lot of patterns and we try to solve, one class of problem, right? There are other approaches where you may need to redesign your whole system, right? Like, for example, your control plane may have bugs, right? Who knows, right? So maybe you should redesign your control plane in a way that maybe using timing or, or other new techniques so that it's much easier to reason with, right? So there are some of the approaches. That's why, like, for example, I was like, we're working on like quasi-synchrony. I think there's some potential there of just making things easier to verify, to reason with, and to think about correctness.
So you could do formal verification of some sort to make sure these things don't happen. You could have like a dynamic recovery process.
Yeah.
Or you could just have a red reboot button. So if you had to choose one, what would you choose?
So I want to answer in a researchy way, if that's okay. So like the reboot thing is tough, because rebooting the entire data center actually would make the problem even worse at some point, because it might just be part of the data center that does not work, but then you have to turn down the entire thing. So verification may help, but it's very hard to reason with and too much effort, right? And what was the other option again?
Like dynamic adaptation. You see there's a problem, so you have some additional processes that can go in and somehow fix it.
Yeah, I mean, to be honest, if you look at some of the cases, sometimes the telemetry actually is a problem. So like for OpenAI, they deployed the telemetry, and that got rid of control plane. So so that could help. I think that's like what's been tried mostly. But I think like the hard part is that we're not prepared for, for example, stability. These dynamic approaches has not worked, for instance. And I think we need smarter approaches in combination with the dynamic approaches. Yet to find out. Maybe you read about it in next year or something.
One thing you mentioned is that these have dramatic consequences.
Yeah.
But one of the reasons why they have such dramatic consequences is because everything is so entangled in few company, right? Like the impression I have is that those risks of failure are always going to exist because there are like new emergent behavior that you didn't anticipate. And so even if you come up with very good protection mechanism, ultimately failures are part of the operation of a network. But when your network carries 40% of the internet, that failure becomes massive. So is the problem solvable only with technical dimension, or is it something that is also requiring to kind of dismantle those like massive stronghold of connection that we have right now?
It's hard to say, right? So, one of the arguments for cloud services is that it's essentially outsourcing. You're outsourcing to the smartest people, supposedly. They are very smart, working on data centers, and supposed to make it really, really good, right? But yeah, centralization. But then at the same time, centralization creates single point of failure, like U.S. East. One is was 1/6 of entire internet traffic or something. That creates single point of failure. But I think the economics has not worked out in a way that would support decentralization yet. So I guess as computer scientists, we're left with the reality, and we have to deal with that, I suppose. Yeah.
So actually, I have a question for Andy and related to this kind of topic. There was a point when Jane Street moved to using Haskell as a programming language for specifications of trading systems of various sorts, which was very strongly typed with very strong verifiable properties. So one of the hard parts in your problem would be how do you specify what looks bad, right? And if you look at how specific trading systems may have been built, they do have formal specifications of boundaries. Maybe that's a way to approach it. I don't know. Any notes from J Street that are shareable?
Just say it.
No comment. No comment. No. So we have gotten a lot of juice out of more formal, well, OCaml and the strictness. I think I'd say that I'm a systems builder first and a programming language adherent second. I'd say that having many different layers with different abstractions and trying to satisfy them all, trying to express your bounds in very different ways, actually is pretty effective. Has been pretty effective so far. But yeah, making good specifications of distributed systems is so difficult these days. Maybe that'd be an awesome place to do more research.
I just have a quick clarification question. So all the examples that you mentioned, the internet as an infrastructure was working just fine. The physical infrastructure. It was always an application or service that causes these issues. Is that what you mean by? I mean, I'm just trying to clarify fragility of the infrastructure. You mean? Because you could go further that the internet as a physical infrastructure doesn't work, that it's, fiber is cut, nothing can be transported. That was not the case in these examples that you mentioned.
No, I think the
network is
hardware
fine.
works fine. Yes.
Okay. So, but that other more physical, fragility also exists. So the problem is even bigger. It's just that the examples that you mentioned typically have to do with software. These are software issues.
Right. Oh, fundamentally, they are. Right. Yeah. I mean, there are cases it could be caused by some hardware problem, right? For example, it can be like part of the data center got overheated. That could cause a downstream effect on the software. That is possible. But most of the cases, if you look at them, are software, service level cases, yes.
So why does the internet always work? Do folks know the answer? It's like, did you learn, huh? We solved all the problems. No, it's because the bar was set so low, right? It's a best effort network, right? It pretty much, as long as a packet got from point A to point B, you said it worked. There's no rules about the timeliness or the required throughput or anything like that. So you're putting on additional requirements that are important, that are needed, and so those do need to be looked at. I would agree with you. And I wouldn't use the internet working as an excuse to say, your problem is trivial or not important because, we built a system that always works. It's just, it was a very low bar for getting it to work. So not that it didn't require thought, but that was like the most ingenious part about it was the network will offer the least amount of guarantees possible, and then we can claim success and let the applications worry about the difficult part. Yep. Come up.
I'm going to respond as
yeah, still come up.
Sure. I mean, I guess a comment that I wanted to make, maybe more specific. I think part of the problem too is that, like companies, even now, like startups and things like that, they all have like this, like their motivation is like they want to get a working software. Like if they're providing software as a service, like they want to
sell this to a customer as soon as possible and like have like a minimum viable product. And so like that kind of means they cut corners too in their infrastructure. Like I was a part of a startup like I was an intern last summer, and they had like an absurd amount of problems with like their original setup that they were actually trying to like move it into a new environment, and that was costing them money because originally they just tried to get like a product that they could sell to clients and customers, and that is like I guess part of the problem too. Like you want to sell to customers, and that means you cut corners, and your infrastructure has a lot of holes. So I think that's part of the issue too, is like they just don't invest in it at the beginning and later have to kind of like patch it, which doesn't really work, especially with like network complexities and like trying to connect different like environments. It's like just, it gets really messy really fast. Comment.
Thank you.
The topic? Yeah.
I wanted to say something as a follow-up to what was just said about misaligned priorities. And I think there's a very interesting project that we're starting to work in Princeton about the AI chatbots and the kind of traffic pattern that they present these days. And so a lot of the work in the networking community is on actually how to train the AI models very scalably and so on and so forth. But not a lot of attention has gone into how the application actually delivers the data to end users, like over the wide area. And an application like ChatGPT actually sends an insane amount of data just for one single text response. So if you make a query, it sends so many tokens and what it is thinking and all of that, which creates a lot of load on the network, which we are just starting to understand, or some of us have just started to investigate. And going back to one of the themes before, which was how underdeveloped regions are affected in many cases, like this is going to put a lot of load on the network, especially for people who already do not have access to very high bandwidth connections. So I guess it's a little bit of a call to action, a call to arms for people to study this as well in the LLM context or in the AI networks context. So yeah, there is that. One other thought I had from before was Dan mentioned delay tolerant networking, and my undergraduate thesis was on delay tolerant networks. And some of the experiences we had in NIT Durgapur in India and IIT Kharagpur, these are two universities collaborating on technologies using delay tolerant networks. And so one of the projects they had, which was funded by the government of India, was building a post-disaster recovery system in areas like the Sundarbans, where people, like there are floods or there are cyclones, hurricanes, and then everything is wiped out. All the communication infrastructure is wiped out. And so can we use delay tolerant networks to restore some sense of sanity, especially to help disaster recovery teams to do some of their work? And a lot of that work has been published in venues like PERCOM and UBComp and so on. So sometimes I think when we say in networking, there's not a lot of work on like sustainable development or like focus on underdeveloped regions. We're perhaps not looking at the work that is getting published in sister venues or sibling venues. And so maybe expanding the horizon a little bit is also very necessary. I said a lot of things. Any response to any of that would be great.
Anybody else?
Just going back to the underdevelopment world problem. So one of the things is that there are no measurements in these parts of the world. So if you have time, so I think it's last November in Hotnet, Theo Benson actually went to Africa and did some measurements and saw that a lot of the internet infrastructure in Africa is actually foreign. They're going to DNS servers in Europe and stuff like that. So it is interesting paper to read about what's happening there and what should be done in order to observe the problem before trying to solve it.
So work is being done. You're just looking in the wrong places. But I guess it is a question. Why are the quote unquote mainstream conferences not interested in this other stuff? Why is it? I was, in fact, saying at lunch, there's a lot of, congestion control for video. There's in fact one in NINES. Why is this in some sense so highly emphasized? Whereas there are lots of problems that lie outside the mainstream that we tend to ignore simply because they are outside the mainstream.
One of the things I think Theo's talk really exhibited is that getting any kind of infrastructure outside of the realm of the usual places where we have measurement infrastructure takes much more effort. So you have to actually go there, you have to build the trust and so forth. And one of the challenge you have is that sometimes when you're reading this, you're like, well, you just did a field trip and you got like 5 right path last probe. But connected, is this really a research contribution? And I don't exactly know whether it should be considered or not. But I do think that it would be refreshing to also get some of those talk at SICOM, which is supposed to be kind of the, and I think that's also one of the point of NINES. So it's supposed to be this general, like, here is all the type of research that is happening in networking. It is important, it has value, and ultimately we have been kind of relying on the same set of measurement to make our finding about the internet. Sometimes these are very biased and skewed. So I think that's.
Since the topic of underdeveloped countries is coming up again and again, I wanted to mention 3-4 orthogonal points. One, if you look at the econ community, they've done a phenomenal job effectively starting developmental economics as a separate sub-discipline within econ. And some of the top faculty in economics across a lot of places have specialized in developmental economics and have made that into a career, right? So a lot of economists cared about development, and over a 20-year span, they've actually made developmental economics as like a career. Second thing that they did, which was phenomenal, was they had a way to get the eyes and ears of philanthropists to get massive funding routed for the style of research, right? I've had the opportunity to work with economists, and for them, getting a 7-digit check to run a project at scale is actually not hard compared to the same computer scientist trying to write a grant to get, I have a new technological intervention. So that ticks off 2 boxes. How do you set up a discipline? How do you get funding? Third part is, how do you actually say something is fundamental, right? Here, you really need to change the rules of the game, right? So for example, when we set up Compass, I actually had to coordinate with 6 to 7 separate communities within computer science who were trying to do AI for social good. KDD had a social good track, and I asked all of them to cancel their conferences to effectively merge them into a single community. And that was a lot of political dialogue to get them to get, and we took over SIG-CAS, which is Computers and Society, which is one of the oldest SIGs that nobody cared about. And it did not have a conference. So now we made Compass as a SIG-CAS conference. And it also set up a pathway. They wanted a journal, so we set up a new ACM journal, right? In fact, ACM leadership said, we need to observe this conference for 10 years. And then one of the ACM editors said, you can actually submit it as a separate journal. You can avoid the Packham process. So we did that, and we had a journal because social scientists wanted journals. So some of the streams are also set, right? Now people are getting tenure, and people doing developing country research. 2 of my friends have also won a MacArthur doing this kind of work, Bill Thies and Nikki Dell, right? So, and in the last 5 years, there have been only 6 or 7 MacArthur awardees for all of computer science. So getting 2 out of 7 is a very big deal in that realm, right? The last part is, how do you actually tie it in together to say that this is actually having an impact, right? There's no point just writing papers. So in Compass specifically, there are many people who don't even write a paper before actually having a deployment. So as researchers, you need to have the discipline that you need to go spend time there. You need to build relationships, work with that community, and actually prove that what you're actually doing. So the onus is much higher to write a paper. But if you're actually hiring for a job, you also need to realize that these people might write only 2 papers, 3 papers. And that kind of hiring culture is there to some degree in SOSP, OSDI, and to slightly a lesser degree in SIGCOMM and SDI. But it's clearly not there in ICML NeurIPS. You need 15 papers to get a machine learning job these days. So you need to kind of balance it out. But I think we just need to think like the economists. And if we strategize and put it all together, I think we can totally do it. But you can't, think about NSF as the funding mechanism for some of these kind of things. So
let me ask a question to the students, and preferably even earlier on in your career, but at any point, it's fine to have your opinion. What is your idea of a good problem? Generally, I mean, is it something that your advisor just says, yeah, work on that? Or is it something that will make a big impact in humanity? Or is it something that's more likely to land you a high-paying job? I'm just curious what your thought processes are. If you're willing to open up and admit, or do you not think about it at all? Do you just hope something's going to, strike you and it'll just be a great problem? Going for a PhD, get used to speaking to a crowd.
Okay. I'm a first-year PhD, so I think I am kind of like the target audience of your question, I hope. So
actually, just going back to Laksha's proposal, what's your name?
Sorry, I'm Sunny, and I'm from Colombia, and I work with Henning, who is not here today, unfortunately. But I was really grateful to hear all the conversations, and I have a slight confession to make, which is I actually never took a networks class until I got into my PhD, and I used to do more like NLP, so like I submitted to the ACL and all those venues, so networks is really new to me. And the reason why I came into this field was actually because of a lot of issues people brought up just now. I think I haven't read the paper, but I know Lockman had a paper about internet access in Ukraine. And I think these geopolitical issues really shed light on a lot of things we take for granted, like the internet, especially we live in a big city like New York, and realizing how, I'm so sorry I didn't get your name, but what you said earlier also resonated with me, because I also come from a country where like typhoons and cyclones are super common, and how do you do post-disaster recovery work? And I realized I should have network fundamentals down and like this like large scale systems thinking to actually solve these problems. And that's why I'm here. So I'm kind of working, I guess, in some way, reverse engineering, understanding the problem I want to solve and realizing I need these technical skills. So very happy to be here. Thank you.
Welcome. Anybody else? Not everybody, Sunny, was it? Yes. Not everybody can have the same opinion as Sunny, so you probably have a different opinion. So anybody care to? Yeah, Cyrus.
Hi, I'm Cyrus. I think another aspect that makes a problem at least fun to work on, or something that's sort of exciting about it, is if something has just been proposed, or like someone has come up with a solution for something, and then you could say, oh, that's a good solution, maybe we can reapply this somewhere else, or like this solution also brings with it other problems with actually implementing that solution or putting that solution into place. And it's maybe not as like nice of an answer as saying like this is like the most fundamental real problems we need to solve, but getting to like sort of benefit from like the just the motivation of someone else saying, here's a problem, here's our attempt at solving it. And then you could just say, great, that looks like a good start. Maybe we can keep moving in the same direction, or even taking the progress that was made in that area and using some of the same ideas and applying it somewhere else. So like that's just sort of that's also maybe partly against what you were saying, which is like, this is why there's this whole mainstream area of research, because things can kind of like bounce off each other and you're sort of like self-validated by saying, well, this idea was in SIGCOMM, so it's an important idea and maybe I can keep extending from it. But there is still some benefit to that, of being able to say like, I understand, like there's this positive work in this direction, I can keep working towards that.
Yeah, good point. I mean, this is why we have conferences and why people publish papers, and you know, you're just supposed to read widely and get ideas from them, and certainly, yeah, translate them into your way of thinking about them. Which I'm just reiterating what you said, does create this hive mind part, but again, it's good to do both. It's good to follow the trail and just, you know, try and take small deviations from it, and also just to say, what if I plunk down somewhere totally different? I think they're both valid approaches. Anybody else? Yeah.
Hi again, everyone. I'm Wahab, Columbia University third year PhD student working with the Costis. I'm a low-level systems guy doing that type of stuff, networking, scheduling, virtualization. So I want to just mention 2 points from my personal experience. Like you can think about it. These are just my 2 cents. A friend of mine, I'm answering the question about like, what do you think it's worth to work on that or not, like a problem. A friend of mine told me once that, you know, like if you think about a problem, like company like a Google or Nvidia can dump engineers and solve the problem in a week, never to work on that. And I get this opinion and like try to always, when I'm like betting an idea that it's worth, let's say, spending a couple of months on that or write a paper, I always ask this question to me that like, let's say Google tomorrow decides to do this, can they, if they solve this problem in a week with a lot of engineers, like then what I'm doing this? If they needed that, they would have done it already. And that's one dimension that I most of the time look at the problems. Another thing is that I know like at some point you maybe like for my PhD that when you arrive, let's say culmination points, for me it's the third year most of the time, you know, like first year, second year you are new to the field, fourth, fifth you are end of the tunnel. So like this is that type of, you know, like the tip point of the...
Don't be too sure of that, but okay, go on.
Yeah. You start thinking about, you know, like at some point you feel exhausted about finding new problems. What I have done so far is that, you know, like looking at the old systems problems, let's say all the papers that like people published in the 80s, 90s, I don't know, like early 2000s, and like being a little bit critical in the sense that, okay, there were assumptions at that time. Do that assumptions still hold or not? For example, like if you look the evolution of the storage systems, most of the systems are built in the 80s, 90s with the assumption of that, you know, like HDDs are spinning mechanical devices, so it's slow to do, you know, like slow to do random access, sequential address is good here. Like the whole operating system of the like the virtual file system, for example, is designed around this idea. And later, you know, like this SSDs came and there was this discrepancy between the programming model of these two devices, and actually the systems still operating today are built keeping the HDDs in mind, which actually don't work that well with the SSDs, and a lot of papers have been just built on this fact. Like what if like later, like I know a couple of papers were written when the PM came out that, you know, like now you can think that, okay, initially we're thinking that the RAMs are volatile, so like we have this fault tolerant system design, like about the synchronization and so on. Now we have a RAM apparently which can, you know, like stand the power loss. So what type of systems we can design? And I think, you know, like if you look at how the like some disciplines evolved over the time, it is possible to find, you know, interesting problems and like maybe solve the old problems with the new status quo. Yeah, thank you for listening to me.
I definitely agree with that. There's certainly been times in my career where I made assumptions about the way systems behaved, and somebody wrote a paper and said, now we're going to make this other assumption about it, and it's a game changer. And to your point, hard drives are often replaced with solid state devices. And that changed latency and other factors that I just always assumed, this is the paradigm the system works in. And yeah, as technology evolves, you have to rethink what the rules of the game are. And sometimes the most interesting papers are the ones that tell you, no, the way you've been thinking about it is no longer applicable. Now there's a new paradigm.
I think it applies for the ML also. Like, I'm not an ML guy from the nature. Like, I have a limited understanding about the stuff happening there. But like, if you think about the most of the stuff, the fundamental theoretical stuff, like mathematical things, are maybe like dating back to, I don't know, like late 1950s, 60s, something like that. Then like, even the state of the art stuff nowadays are not that new. Like they are made a long time ago. For me, the main enabler there was the hardware that, suddenly like the devices became so powerful that you can do this huge number crunching operations. That was the main enabler instead of, this paradigm shift enabled them to, like designing these systems. So yeah, that shift is, I think, is more important. I think in economics, sometimes they call it black swan. There was this guy called Nakim Nicholas Taleb, like writing the book about that. Basically, the idea was that if you like try to see something that the most people don't see, then you can catch a flow from there. And I think, like it's the main thing about the PhD. Somehow you need to, like find some flow that, you can keep doing work out of that.
So on that note, well, actually, are there any students from any other universities that would like to comment? I think we've had 1, 2, 3, 4 Columbia students come up. So anyone from NYU or Princeton or UPenn?
Just on the topic of choosing good problems, I think one of the ways that I chose some of my problems or got prompted to by my advisor sometimes, as well as sort of leverage the quote unquote unfair advantage that you have in a particular location. So, I mean, whatever is the infrastructure of the lab that you're in, whatever is the expertise of your advisor, whatever is your background, whatever motivates you and has motivated you in your past research during undergrad or master's. So a confluence of those things usually tends to be something that has motivated me. So I often think about that phrasing, unfair advantage. And I think it's not new to anybody, but that's kind of a framework that I like and has helped me quite a bit.
Okay. Hello, everybody. Thanks for this nice workshop conference. I am Samuel, a PhD student at NYU, and I'm also from Colombia, but not the university, the country. And what? Paisa? No, not Paisa, but close enough. Yeah. I'm from another region. Paisa is a particular region of Colombia. I just wanted to comment on what I think it's a good problem. And I just started my second year of PhD, so I'm definitely open to be totally wrong on this. Please correct me, any of the more senior faculty here, if I'm wrong. But I think a good problem, or at least what I believe so far, it's a problem that strikes a good balance between what interests you, what motivates you, and what has a potential of having an impact. So if we put that in some kind of graph or like an axis, it should come close to the origin in some way. Now,
no interest.
Well, yeah, like no interest and impact at the same time, like some kind of balance between those. Yeah, for in the x-axis. Yeah. Well, yeah, x and y. Yeah. In fact, yeah, it should be like in the lower. Yeah. Exactly. And what if now the challenge as a first year PhD student is that you probably don't know what's like exactly what's going to be impactful in a particular field. But what I've told some students that, for example, applying to PhD these days is that you also have to be you also have to be open to new problems. A lot of students that are applying to schools are thinking that they want to do a particular field or they want to do focus upon a particular problem. And they are not open probably to the idea of finding interesting problems in other fields, or using within a field, just finding another problem which might broaden your horizons and actually make you learn much more in some other problem. And I think that has been my experience in my PhD as well. I'm working right now in problems that I didn't think when I was applying to PhDs, but has definitely broadened my horizons and have made me learn a lot. So
what kind of problem?
Yeah, I'm working, and actually not in networks, but I work more like in deep learning stuff for astrophysics. And before I've worked on a different field of astrophysics, which is X-ray astronomy. And now I'm working in the sun, which it's totally different because the X-rays look at very, very far away stuff and the sun is very, very close. So the kind of measurements and stuff that we do for these kind of different things is very different. But I've learned a ton. And yeah, I just wanted to say that. That's it. Thank you.
Anybody else?
Hi, I'm Karan. I'm in my final year right now, so I guess I'm looking back to like the last 5 years of my PhD. So in terms of which problems to work on, like initially I felt like we should work on problems that are more fundamental, can really change the game. But then I realized, like, at least in my experience, the papers that got accepted easily to like SOSP or VLDB, like on the first time, were the papers that I felt were more like marginal improvements over the baselines, like a 10% or 20% improvement. And for example, like the paper that I talked about today, I felt was more fundamental. And that has been like the most difficult paper to get into a conference, which is why I was thankful for NINES, because it does prioritize like fresh ideas. But then I feel like this community and the reviewers at like NSDI, SOSP, OSDI, they kind of discourage, even though in the call of papers, you will see like these conferences like SOSP and all, they say, we prefer work that is more fundamental as opposed to incremental. But in practice, for me at least, it hasn't been the case. So that's something that I found really annoying. Like we should do the opposite. Like reviewers, I think, should be more considerate of PhD students and academic labs who may not have the capacity to like run huge deployments and do all the experiments that you would ideally want them to do. So I just wanted to get people's thoughts on like, how could the reviewing community change such that, I mean, NINES is good, but like even at the existing conferences, like the old ones, like NSDI, SOSP, etc., like even for these ones, is there a way to make it such that the reviewers kind of are more considerate of which papers to take in and which not, I guess.
Sure. I have a zillion thoughts, but anybody else? Why is this happening? Why do you think it happens?
A very quick thought. I mean, apparently, from what I've heard in PC from people who've been doing PC for years, is that it's the younger crowd that tend to be the harshest. And I think that kind of illustrate the fact that we are frustrated and we kind of continue to pattern of frustration. So I think it's part of education in a way. It's like, how can you be a nicer reviewer? How can you train students to be cognizant that there are students on the other end and so forth that they have tried? And so yeah, I think the like one of the core problem is really that we come in as PC with our baggage, and it's hard for us sometimes to process that in a way that is healthy. That's one thing that I think.
So I'll say historically, I can recall that there was a time when people did not get credit for doing detailed work, and there was a sort of a complaint in the reviewing process that there are these people putting in a lot of effort to really lay down all the details and be precise, and they're not getting credit for it. So they should be given more credit. And then I feel like the needle swung in the complete opposite direction, where now that's the primary requirement. And the idea itself often tends to get buried because you can criticize, you didn't study this enough, or you didn't study that enough, or here's a corner case that you didn't consider. So just historically, that's my sense. Any thoughts on how to fix the problem?
I mean, I can say like, if I like, hopefully when I graduate, I might be invited to some PCs. Like, I would first try to like evaluate the idea of the paper. I guess similar to maybe the NINES idea, and then I would see like which experiments they did make sense for the model or like the framing that they're considering. Like, for example, like for some of my papers, it was meant for like a billion user like deployment. But of course, like at Penn, like I'm not like Google or Meta, I'm not able to do that. So we had to do like simulations and extrapolate to this large scale. And so, for example, like I would try to be considerate in that sense and be like, obviously, it may be difficult for most people in research to do that. So are like some experiments that they are doing like realistic? Or is it capturing like the core idea, and is it like benchmarking like the main things that they should? And I think if the idea is good, then someone is interested, they can always implement it like later. I don't think that should be, even for systems conference, I don't think that should be necessarily the primary way to say whether you want to accept or reject. So I think that's my first thought. I mean, I don't know. I think this could be a lot of politics as well in this species, like I have. Yeah. And also I wanted to add, for in terms of which ideas are more interesting. For me personally, I had a systems background in undergrad, and then I learned about like cryptography in my PhD. So I felt like marrying like two different areas, like the systems and crypto, for example, could be networking and ML. I don't know, like these two, like two different areas, combining them into like a paper, for me felt like the most rewarding. So if there are fresh or like new first or second year PhD students here, my 2 cents is I would encourage you to like learn a new area that may be unrelated to your current area, and that could open up like a lot more possibilities. You may even be like the first person to work on that paper.
Anyone else?
Just very quickly on how to solve the problem. I think leading by example is a great way, and NINES is doing that. And I think one great thing that I have liked about NINES is the reviewing process, where reviewers essentially basically discuss on a Slack channel, from what I've understood. And then there is one consolidated review that really focuses on the key points being made, and the shepherd really makes sure that those key points are addressed, and the more sort of minute details can be treated as less important in this context. So I think this is great. I really like the fact that NINES is trying to lead by example, and I think that's going to be very powerful going forward, or at least I hope so. So hopefully that changes some of the trends in the current conferences.
I'll just add, NINES asked for feedback on the reviewing process, and I told them I thought better than this summary of what the discussion was, why not just run it through an LLM or anonymize it in some way and just reveal the discussion? I thought that would have been much more interesting to see how the reviewers interpreted what you did, both for accepted papers and also for not accepted papers. I mean, really seeing that discussion would have been useful. So they probably won't listen to my idea, but I tried. Anybody else?
One thing that'll be really interesting for the community, TMLR tried this, but if we had a notion that a publication is not really a publication, but a timestamp on a document, and had a notion that you actually publish something and you get an invitation slot to just come and talk about it at some particular point. But then the onus is on the authors to make sure that they actually are able to incrementally fix the problems. Then effectively you get the inverse game, which is many ideas are out there and only specific ideas really are able to percolate, but it becomes a more, there's larger democracy at play, but how will it actually have an inverse effect on quality? So if anybody has any thoughts on that, that's something, because NINES is a new venue. you could change the rules of the game. You could actually say, so TMLR has a policy that if a paper is technically correct, they will take it. It's not going to be how interesting the topic is with respect to machine learning, how hot the topic is, and so on. If you submit to NeurIPS or ICML, there is like a flood of how hot the topic is defines whether the paper is going to be accepted or not, and so on. So if people have specific suggestions like that, it's good to collate them and share it with the NINES community.
Any other comments or questions? Okay. Oh yeah, sorry.
I just thought about what you said about the needle going the other direction. So I think this is part of the maturity of the field. 20 years ago we were less mature, and there was the experiment stuff that I think that this is kind of block a lot of innovation sometimes because you have a very high bar of experiments. So if we could, like back in the day, like 20 years ago, like a paper could have simulation and it was perfectly okay, and it wasn't networking wasn't as system discipline as it's now, and maybe we need venues that will provide less fully executed fully executed systems or fully executed frameworks, but ideas and innovation that are supported by simulation this time.
Any other comments? Okay, I was going to throw out a crazy idea. So I spoke to a neurologist once, or someone who studies a neuroscientist, and he was explaining to me the way neurons work. And the way neurons work is they fire, right? And that it helps you with your interpretation, but it's also they fire at different rates. So, and the way he explained it is when you look at something and you see it, the information about that something comes to you at different points. Like I could look over there and see yellow and then start to put together there's a door. And then, in some sense, the information is reaching me bit by bit. And the longer I stare, the more I notice. So like more neurons are firing. So in some sense, that's a networked system, right? With delays, and the delays actually are utilized in some way. And assuming LLMs are not the final step, which is what some very smart people like Jan at NYU tend to think. What will be the next step in artificial intelligence or heading towards superintelligence? And will it be this neuron kind of model? And will networking and latency play an important role? Any thoughts? You could build the first networked super intelligent thing where the network latency actually plays into the intelligence of the system.
One thought on this is, there is like this increase of multi-agent, and you're getting to a point where you essentially have so many agents that it's like almost a network of network. Maybe that's like a version of the superintelligence that you're talking, where you have like specialized agent on specific task, and like when you combine them all, you get this superintelligence. I know some people disagree and don't think that this is the way forward, but this is one direction that has appeared. And when you think about it, it kind of looks like the internet. So you have a like distributed system where with like
you're talking about a human like.
I'm talking about essentially multiple agents who are each LLMs communicating on a specific task and being separated within the same data center, but essentially having like to collaborate in order to reach consensus or respond to specific queries. Like this is a direction that we're seeing, and when you're getting closer and closer to like a network that might look like the internet if you think about it, where you have like specific networks with their own like rationality, own decision making, and so forth that are communicating with each other. And so that in a way there are some parallel. That's a direction people have considered for superintelligence. That essentially the way you can get superintelligence is having many agents all fighting for the right response in a way. So I do think that this goes toward what you're saying, that it might be actually like a network system the way we have been thinking about it for the last 20 years.
Like multiple LLMs or?
Yeah, multiple LLMs. You don't buy in that
I mean, I know nothing about it. I mean, Jan LeCun seems to be a smart guy. He doesn't think LLMs are going to take us all the way there. I'm inclined to believe him more than Zuckerberg. So that's just my opinion. Anybody else care to say something outrageous or?
I mean, I have sort of an adverse reaction to this, super intelligence stuff in terms of, I think we have really no idea how our brain works to that detail that would allow us to say, oh, now we understand how it works, and now maybe we can figure out how to mimic it and actually get some learning done. I think we use this language, this terminology in terms of learning. We developed a learning model, but the model doesn't really learn anything. I mean, you feed it some training data, and it processes this data to some degree. There's learning is really a term that shouldn't be used in this context, but it's being used. The models make mistakes. Clearly, we don't call them mistakes. We say these models hallucinate. So you build a whole language around this sort of framework of machine learning that has this appeal. But when you sort of dig deep down and sort of say, it doesn't learn, it does mistakes, it does make mistakes. What do you mean by super intelligence? I mean, I just have a hard time to sort of see that we will be getting in this sort of space very far, very quickly, because we just have no idea how our brain works. So let's first figure out how the brain works.
To that point, I wish I knew the paper, but there's supposedly a paper where they took these neurological models and they used it to describe a microprocessor, and it got it all wrong. So, because we do understand how microprocessors are built, and it's just the way it tried to explain how it must achieve what it achieves was just way off track. So yeah, absolutely, we have no understanding of how the real brain works and what it means to be super intelligent. I completely agree with that. If there was a solution, it would be a network solution, right?
So maybe just in this context, I want to throw out one maybe statement that sort of I may get some reaction. So to me, the area of AI for networking is a direction where we say that's the end of science to me. The way we are doing this, because we are not asking any more fundamental questions in terms of, so you have a model, you don't ask anymore, why does it work? How does it work? And when does it not work? Unless we ask these questions, what does it mean you developed a model that is accurate for this particular problem 99%? The science would dictate you have to understand why it works and how it works and when it doesn't work, and we are not there at all. So to me, this sort of current development of AI for networking is the end of science if we continue that way.
Anybody care to disagree? I mean, in some sense I agree with that, but you just said we don't really understand how the brain works, and yet because it's ours, we do believe it does have intelligent capacity. I know you all think because I think, and I don't believe I'm just living in a simulation surrounded by avatars or what have you.
So what is the current AI for networking trend? I can think of congestion control algorithms, like developing topologies based on like AI models, etc. So what are the actual fields where we might be using it?
One field of, where you see all these activities, security. cybersecurity.
So in terms of recognizing patterns,
all different kinds of attacks, and here's a machine learning solution for this attack, for this attack, for this. And you look at these conferences that are full of those papers, and I guarantee you that if you pick up one of these papers that is accepted, reports great results, and you dig in and you look at how does this model make the decisions. It didn't learn anything about the attack. It figured out something in the training data that is an artifact of the data. It basically cheats because it finds a shortcut. And most models do it that way. There's no learning going on, but these papers are being published. And so, and in larger and larger numbers. And, I think Europe's is an example. 10,000 submissions. And so if you don't start asking these more fundamental questions, this avalanche will continue. And the only way to weed these things out is don't submit a paper that doesn't tell me how this model works and why it works and when it doesn't work. To me, that's the only way to stop that avalanche from coming or from continuing because it's already in progress. But
yeah, I guess I see it as like two streams. There's the science to understand and gain knowledge on trying to understand something, characterizing something. And then there's the part where you're solving a problem.
Right.
You're trying to solve a hard problem, you're applying something. And I think these fall into the later category where you're trying to solve a problem that is harder to solve. You use a solution that you don't understand, but it solves the problem for you.
Well, solve.
Yes, in some form in some form of approximation, it solves it for you, I guess.
Nobody in their real mind, like a cybersecurity analyst, none of them would put that solution in the network because they know it doesn't work.
Yeah, of course. And then it's a flawed solution. Then maybe one needs to think about whether it's like a valid contribution. I don't know.
A much deeper version of your question, which actually bothers me a lot, is when we talk to students and they start using a variety of AI tools and so on, especially when I look at students at undergrad level, master's level, or sometimes now even at a PhD level, we produced very deep thinkers with respect to how you think about a particular subdomain. But when students start using a lot of AI tools, a lot of thought process has gone one level higher, that when you go deeper, I'm actually seeing large volumes of candidates going through my startup interview process who don't know how to code for getting jobs. And very high caliber students in resumes, but who are not able to pass like second round types of very detailed thought process in interviews and so on. That ability to deeply think about something, we are losing that thought process. And when I see my 8th grader son using AI tools, I fear even at a middle school level, some of that deeper thought is slowly getting erased. So I'm genuinely worried about like future of learning and how we are basically succumbing our own brains to a particular line of thought. And we are losing certain critical thinking abilities, and that is actually going to affect humanity in a very big way. Especially if you want to go very deep and actually do something completely different. And if you're just going to throw AI tools on top of AI tools, that really deeply worries me about how society is progressing.
On the other hand, those of us who are old and getting older and starting to lose our mental capacity, AI is great to help us maintain our productivity.
So to your point, like there's a recent paper from UC Berkeley where they use Alpha Evolve and Open Evolve. These are like AI tools for research, and they take like a dozen existing published papers from NSTI, OSTI, VLDB, etc. And for each of these papers, the AI is automatically able to improve upon the systems which were previously published. So they asked this question whether like future research in systems and networking will just be like the relationship between like a advisor and a PhD student, where you are just prompting the AI, like this is the problem, and figure out how to fix it, and you kind of iterate with the AI, like similar to, I guess, yeah, how advisors do it. So that definitely had me worried too. Like if I did that throughout my PhD, I wouldn't really have any deep understanding of what I was working on. But on the other hand, I feel conflicted because like if AI can, assuming it is true, I think the paper is not peer reviewed yet, but like let's assume that it is true that it can actually improve on basically like any existing system that humans can come up with. So then like, is there any point of us doing research as we are currently, or should we switch to AI just doing it for us? I mean, seems like a trade-off. Like, so yeah, I mean, it's a very provocative paper. So just wanted to get people's thoughts on like, yeah, what to do.
So I'll just add 3 funny examples. Funny example number 1, ICML is basically now running 30,000 submissions through an LLM review process. And the LLM review process is going to be giving much deeper feedback. And EC, another conference, if you submit your paper 1 week earlier, the LLM review will give you the full review and you get a chance to fix it before you submit 1 week later. Second example, I just finished a bunch of reviews for ACL, and a lot of the papers are using LLM as a judge to check another output from another LLM. And we as a human are sitting in the middle, checking for correctness and, does this paper make sense? So we're already in that realm inside the publication domain. And last funny example, even as part of my class, and some of my students are here, I changed my syllabus to include a bunch of these, GLIA, ADRS, and a bunch of other self-defining systems papers, because even as a teacher, I do not know how this thought process is going to evolve in SIGCOMM and SDI community in 2 years. So.
I mean, it's great that we have people giving opinions, but anybody else want to comment? I think we're still down to like a handful of 7 or 8 people. If not, Walter, please. But
learning kind of with paper writing using ML. Okay. Yeah. I wanted to follow up on this. I have a friend at NYU. He works in the scientific computing ML space. And the way they write papers nowadays is they write an algorithm and then they feed it to an LLM and they say, write the paper for me. And then they do like 5 papers like that. And then they feed the paper that is written into another LLM that reviews it for them. So they get the low hanging fruits done. And then they submit it. And then it's going to be, then you have the choice to have the LLM track, which is reviewers being LLMs for you that review it. And then you have a normal human track. And so they often choose the LLM track because it's just, you have quicker turnaround on it. And so they're producing papers like this nowadays. I'm not entirely sure if I haven't written a paper recently, so I don't know how current students are approaching the, like, if you would write a SIGCOMM paper now, how would you write it? How much would you do using an LLM? How the plots are you using? How much of this content would be machine learning generated versus your own kind of voice in writing this paper? This is a process I'm not entirely sure about, and I'm curious about how students approach this nowadays. Anyone has an opinion on it?
Hey, Sophia, I think this is, I'm from Princeton. I'm in my final year. I've been thinking about this a lot. I think that early on, I was also extremely concerned about all the chatbots and everything, not only for us as a community of researchers, but broadly for the more general population as well. Because I also found myself, going to GPT a lot and just like asking basic questions so that I didn't have to even bother going to Google. I just like ask GPT, it's faster. And it's personalized. That I think that aspect is intentionally very alluring to a lot of people because you can continue the thread. You don't have to like find another, whatever source that you're looking for. But back to the question of writing the papers, my initial response is ideally I'd love to not read AI generated papers like ever because I think they're pretty bad. And I think that you can tell in research papers and like other writing and generally, I've used like full transparency, I've used them because I was like, oh, it's not bad. Like I was surprised that it was like pretty good. But then when you really read it, and if you're somebody with any type of background in that field, you can pretty instantly tell. And that's a very bad look. And also it very easily either hallucinates or ends up going on a whole other track. So I recently was part of a like dissertation writing boot camp because I'm in that final part of my process. And this question was asked to like all the students participating. So this was at Princeton, and these are students from all different fields. So the question was, how are you using AI tools, if at all, in your writing? And it was very nice to hear the different responses. It sounded like students these are PhD students. So we only got these tools like the last couple of years. The undergrads might have different answers perhaps, but it was nice to hear for the most part, it sounded like folks were using it, maybe as a light editing tool, but then you could just use Grammarly or something, which also has AI elements. But basically, you come up with the ideas, you come up with the structure and the flow. You even come up with the like draft per se. And then if you want to feed it in at that point and ask for edits. So kind of like what you were mentioning with the systems is that AI is helpful, at least in iterating, possibly. It's almost like getting a free editor. But you have to be, I think, to wrap up, what can help keep the dangers of AI at bay is to stay very critical of it. And I think that's something that as professors, as researchers, it's very important to emphasize to students because this is a tool that you're not like, it's kind of like a knife. You're not going to just like get rid of it from your kitchen. You have to find good uses for it and then warn people of all the bad uses as well. But I think the way to keep it on the good side is you have to be incredibly critical, keep it out of the early parts of the process, especially writing. Sometimes I will say I use it when I just want to like chit chat with somebody. So I'm thinking on ideas and I chit chat a little bit. Like it's sometimes helpful with like looking up terminologies or like say some type of very initial broad lit review, something like that. But when it's time to actually get down to ideas, like you have to do the hard work. You have to go back to the whiteboard literally and then write up the stuff and then be very critical with even edits that come. So that's kind of been a little bit my experience and also the ways that I've heard some other folks using it in different fields.
We're almost at coffee time. Walter, if you still have the thoughts in your head, please, and then we'll close off. And we managed to get through and not have to watch videos. I'm very happy about that. So I don't know if other people are upset, but you can go home and watch the videos on your own.
Yeah, just a short comment, both to Lakshmi and to what you sort of said. I mean, I think humans will always be better at certain things. We are right now at this stage where we have to figure out what are we better at than machines, and we struggle. We seriously struggle, but there is always stuff that humans will be better. And once you figure that out, then you can sort of say, okay, this is where machines are good at, give it to them, but this is where humans are good at, and I keep that. Now this will evolve over time. This will change. But I think it comes back to what are we teaching the next generation? What capabilities do they need in order to make sure that society is moving forward and not losing the curiosity, for example? Thank you.
At the same time, the evolutionary process, the next generation always figures out a way to do things differently, and arguably sometimes is better, more successful. Take music, for instance, that's constantly changing. So on that, let's have coffee, and then we'll come back and we'll have our Ask a PhD session, which really puts more emphasis on students asking questions about the PhD experience, the process, whatever you want to ask, basically. So thank you, everyone. Give yourselves a hand.
I think so. No, I said. Yeah. Maybe she's talking. Yeah. But maybe it's gonna have this one guy that you were talking about. Oh yeah. For Leo too, or just? Yep. Oh, for the. Something like. Yeah, it works.
The staff.
Okay, this is the quote Ask a PhD session. It doesn't have to strictly be that way. So students who are more senior also feel free to answer. If you have a PhD and you got a question, that's also okay. But the goal is really the transfer of experience and expertise to the younger folks. So there's no set agenda. In fact, Lakshmi was just saying that we should be talking less. So if folks who are new to the PhD or almost at the point of PhD want to give advice, that would be great. I won't say much more. I'm supposed to not talk. So does anybody have any burning questions about anything related to networking, getting a degree, academia, industry? What do I miss from my PhD? Oh, what do I miss during it? Lack of responsibility to anyone but myself, right? I could disappear from the earth and no one would have cared. And that's actually very liberating. So maybe I still disappear from the earth and no one would care, but
I would have cared. Hi, everyone. My name's Harris. I'm a first year PhD student at Columbia. I'm co-advised by Ethan and Gil. My main question was, I'm interested in a lot of different topics, and this kind of gets back to the theme we had earlier with, how do you choose a topic, or how do you choose what projects to work on? So my main question was, kind of how did you navigate that, or to any PhD holder, how did you navigate that through your PhD?
I could talk all day on this. So I'll just say, I had a lot of disagreements with my advisors about what topics were important, what I wanted to work on. I had ideas about what I wanted to do, and they had different ideas at times, and it was a bit of a push-pull. But they were very good at helping me formalize what I wanted to pursue. And also, Jim Carosa was one of my advisors, and we just talk a lot about I thought, I was the critic and he's always very optimistic. I would say this paper sucked. I don't know why it got in, and he'd tell me why he thought it deserved it, and his perspective, and that really rubbed off on me. And I think the message he got through to me was go for the low hanging fruit. In other words, if there was a problem that somebody else had just done and you're trying to do something very similar to that, that won't have as much impact as going somewhere where the tree is still full of apples. And I probably took that too far sometimes, but it's in my head all the time that I should be working on. If I see a lot of people working in an area, I say I don't want to, go there. Like I'm not getting into AI now. It's just my personal opinion. It's too crowded. I'll go somewhere where people aren't working so much. And that's not right. That's just the way I do it.
I will repeat what Dan, my advisor, is saying. Just argue all the time with your advisor. But I think also having different perspective in the group of people you're working with, people who have a different opinion on the way you should be doing things. It's frustrating at first, but it's ultimately very enriching because you realize that good research should be convincing to, or you should be able to convince that the research you're doing is important to a multitude of opinions and people that are coming from very different approach to how research should be done. And so concretely what this means in your case, because I know you're co-advisor, is trying to juggle all those different expectation of what the research should be about and use that as a strength that if you can convince those two people in that room, then it's likely that you're doing important research. So that's one thing that I really valued from my experience, this ability to have people from very different backgrounds still feel like what you're doing is deserving of your time.
You watch a video?
That scared me. I guess I have a question on just thinking about research problems, as in there are problems that are incremental. For instance, I've been working on privacy papers, and sometimes you work on a very established problem that some is easier to get publications and easier to graduate, I suppose. And then there's other set of problems where you're doing something very controversial, doing something very different from what's been thought of for over maybe 40, 50 years. And that is difficult to I guess as a junior student to grapple with. I guess I don't know, I mean, I would actually prefer to do something revolutionary, but it seems terrifying for a junior student to handle. So I wonder what are your takes on this, I guess.
Some thoughts?
So I mean, I wasn't sort of a student or a PhD student at the time when I did my sort of work that looked at network traffic and showed this sort of self-similar scaling behavior. I was working at the company, so it's slightly different. But the experience still is that you are pretty much alone when you go up against establishment, and you really have to have all the ducks lined up in terms of the empirical evidence has to be there, the mathematical foundations has to be there, the statistical tools need to be, pretty solid. But if you have everything in place, then even the established people take a look at what you have, even if it's completely different from what they have been doing, and slowly come around. But you have to take the heat. That's clear. But I think it's worthwhile because it really gives you an insight into how other people view certain aspects of your work that, from your perspective, is sort of obvious why you did it. From their perspective, it's not obvious at all. So I think doing something that is quite different from what the mainstream is doing has tremendous impact and benefits, but you have to be able to defend it in ways that you don't have to defend other work that isn't that much different from other people.
So as a PhD student, it's very important to have 2-3 very basic things that on how you approach research. So especially if you're doing something controversial, highly controversial, and you're having a completely new take, you need to have a plan A and a plan B. The plan B could actually be a completely different problem than from plan A. And one thing that certainly helped during my PhD was I was working on one controversial paper and one completely new topic. And the controversial paper actually got rejected 3 times. And finally, it got into NSDI. And the new topic picked up during that time period, that the new topic effectively became my PhD direction at that particular point. So having 2 parallel problems is not a bad idea. The second thing with respect to a controversial paper is you should do your level best to cover your bases, and you should be willing to take the hit, but you should also be figuring out how you draft your paper, the experiments, so that you can actually so a controversial paper is very hard to write at the last minute. You pretty much have to finish the paper 3 months before, get it reviewed among friends, fix a whole bunch of things, and give it 1 or 2 shots. If by the second shot you've done your level best and it actually gets terrible reviews, you kind of have to figure out a complete pivot to figure out where else you might want to send it, completely abandon it. You need to really take that feedback in a way because people say, 5-year PhD, 5 years is actually not a lot of time. So you need to sort of reverse calculate backwards as to where you are. And you need to get like this thing to figure out what type of job you want. So always having some notion of a career planning is a very important way of planning and getting what you want out of a PhD. That's and you should absolutely pursue very hard questions, very fundamental questions that you are super excited about, but also have a plan B just in case it doesn't work out. One thing I would say, there are a bunch of students who never talked. So and specifically some of them are NYU students. So I will take the privilege of introducing Hasib, Dennis Ripkin, 2 students. Anybody else wants to? So Hasib.
Hello. Okay, so I was thinking about what if this whole research institution is doomed? For example, if you go back a couple centuries, the research was done by priests and, people who are not going to get paid well for that. They're just looking into the future and doing something they like. But then there was some glitch in time and we all started getting paid for doing research. And now agents are gonna do all of it, and LLMs are gonna take over, and researchers are not gonna get paid for doing research. And then again, we'll be back into those time when only people who really care about research, priests, they will be doing research. So in that, I mean, I'm at the end of my PhD. If I was at the beginning, I would probably drop out if I believed in that. I don't 100% believe in that. But what if that is true? What if that's the future, and we have like so much supply of researchers, and most of the things they're gonna do, LLMs can do better. What if that's the case? How do we prepare for that world?
So I'm not so cynical in the sense that, over time you see these claims that academia as we know it's going to end, and it doesn't. So 10 years ago or 15 years ago, these MOOCs, these massive online courses, were supposed to wipe out all teaching, and that didn't happen. So I suspect that the same is going to be true with these LLMs. Maybe we just have to shift what it is we're doing. But people are always going to want to be useful and valued in some way. We just have to figure out what that use and value is going to be. And I'm just from past experience, I'm pretty confident we will. And I mean, there are like tons of examples of this. There was when I was starting as a faculty at Columbia, one of my colleagues told me, internet research is dead because all the traffic you can send, we can already handle, and it's not going to increase. I said, how do you know? Like, how can you predict what future applications are going to be? And he asked me, like, well, what are they going to be? I said, I don't know. But, sure enough, there's always more and more need. So just be optimistic and, keep doing what you enjoy doing. And I can't promise, but, highly likely things are going to work out. Don't be so cynical. Cynics, they tend to put themselves in a corner and worry away, and life goes on.
Yeah, that's what I also say to myself. So that's what,
and that's the voice of that voice on your shoulder. That's the one you should listen to.
I was the NYU student. My name is Hasib. I'm a fifth-year PhD student. I work in networks, mainly financial exchanges on public cloud. Thank you.
Oh, okay. It's me now. Yeah, I'm also an NYU student.
Oh, sorry. The AV guy asked that we get up. I mean, he said he liked that we get up and speak here. It's better for the presentation. So if you don't mind, Hasima, you got to escape it, but everybody else should come on up and talk on the stage.
Well, also NYU student, second year. I actually do not share sentiment that Hasib has. I'm actually quite optimistic, and it's less of a question, more of a statement. I partially think that PhD students are already severely underpaid. And if you actually cared about money, you would probably go to the industry. So I already think that people who do it because they're really passionate about it. And, you can probably just take away all the money, and I don't think much would change at this point. But I'm actually excited about LLMs. And I know that there's quite a few people who talk about LLM doom and how research industry might really suffer from it. I tend to be an optimist from this perspective, and I do think that LLMs, as any tools, can really be used to improve the quality of the research. For example, I recently talked to some Siri guys who really hate coding, as I guess somewhat common for Siri people, but they've been able to create quite a few tools for them to really showcase their experiments and just really visualize whatever they've been doing, which otherwise would have been really unhelpful. For me, I personally find that when you use it properly, probably just don't overly rely on it, but as long as you can just make it modular and utilize it in the right ways, it can boost your productivity significantly. So yeah, I think that Overall, it's a good thing. And as any tool, you just need to learn how to use it. Well, anyone else wants to add anything?
I'll say just on the PhD students or underpaid issue, Columbia, when we leave food out, it doesn't get eaten. And I always say to my colleagues, we're definitely overpaying our students. If they were, being paid right, they would be going for this food. And when I was a PhD student in my early years, I was on a 3-day rotation. I was ramen, spaghetti, mac and cheese. And because there were 7 days in the week, that left 1 day for my extravagant meal at Burger King. They had a $1 Whopper on Tuesdays, so I'd go there and get that. And I put stuff in my ramen and my mac and cheese, so that had some healthy component to it. But an egg, some scallions, yeah. Hot dog in the mac and cheese.
Spicy ramen or not spicy?
Whatever was cheapest at the supermarket, the ones I could buy in the big boxes for, $3 for a pack of 30 or whatever.
Yeah, but now that I get to visit Jane Street office, I would really love if you also had fridges with all the free drinks.
Yeah. So finish your PhD and get a job at Jane Street.
I mean, we have a fridge with like a couple of beer staying there for a few months. I don't know. I guess at this point it's up for grabs, but that's the only free drinks I've seen there.
What kind of food do you leave your students in Columbia?
Well, okay, so
You want the official or the unofficial version?
our group has a weekly lunch, and I insist that they go for the lunch special wherever they can order from wherever they want, but it's got to have a lunch special, and you got to order off the lunch special. I'm just trying to teach them to be frugal.
But we've tried the omakase lunch special. It didn't pass.
Yeah, we actually have a couple of paper presentations, and we try to learn more PhD students with promise of free food. We essentially do Chinese takeout food, and everyone who can come and present paper, they can just come over there and just make their PhD survival a little bit easier by saving on lunch that day.
Well, I mean, I'm open for negotiation. So, if you guys want something free, then I'm going to place my requirements. Maybe we need more papers published, or, guys, if I show up at 8 at night and you guys aren't here, that's no good, so. But we can haggle.
One thing about all of the anxiety you might feel about LLMs and just the state of the world and so forth. I think that there are two things that are reassuring to me. The first one is that there is enjoyment out of understanding things deeply. Ultimately, one thing that you have to learn, I think, as a PhD and as a researcher, is that the end result might not be what you expect. If it is, then that was probably too easy of a problem. The learning process, the creative process of finding the right question and then experimenting with it and so forth, this is something that should bring you a reward by itself. If that's not the case, then maybe you're not looking at the right question. You need to have this dimension. The second dimension is a lot of things are outside of your control. You're going to submit papers, and one PC is going to hate it. The other one is going to love it. Sometimes you're going to get in this really awkward situation where 2 members of each PC is going to love it and it's going to get rejected twice. And these are things that are outside of your control. The only way you can be okay with them is by accepting that all of this is random. I mean, for me, that's been extremely helpful to say, all the process of getting my ideas accepted and so forth is random. What isn't random is making a convincing argument in front of my collaborator that I have an idea that is worthy being pursued. That's something you can control because you have this back and forth, you have this conversation. So ultimately finding satisfaction out of this, I think is what is rewarding, is what makes me want to continue doing research. I'm going to paraphrase Philippa, who was saying one important thing you're doing research is doing it also with people you like. And I do think that this is also really important. It's where academia is one big happy family. Everybody's friendly with each other. We can talk about deep problems, and it's great. It's amazing. And as long as we continue this collaborative mindset and we try to
continue building together, I think there is going to be value in still having a bunch of human in a room discussing things.
I'm hearing a lot of optimism, and that's great. Maybe I wanted to just like maybe mention just a little bit of like where these anxiety may come from, and like one of my concerns of AI, for instance, is that it's not exactly as like good or bad at this stage, right? So I would try to have it write paragraphs. It's actually pretty bad, really bad. I mean, it can write stuff, but it's not to the point. It's not the way that I would like it to be. I guess what has been concerning was just really the pace of development rather than like the absolute raw intelligence or utility of AI. I guess like I remember in like 2020 when like ChatGPT came out in like 2022, if you're using it, you're just like really cutting at the bleeding edge of AI, right? And then like and then coding tools came out, and like if you're not using cloud code, you might not be at the bleeding edge. Now these days there's like 100 frameworks uploaded to GitHub every other week, like 30,000 submissions to NeurOps, right? Like where do I even start to understand where the field is, right? I suppose even people who are in the AI community doesn't even know like where things are going. So I guess like it's just a sense of like, so it's like as a PhD student, like for example, I work in systems. I would rather catch up on like SSP, USDI, right? I have other things to worry about. But it seems like if you wanted to really, like just not being, like behind too much on these kind of things, you have to. It's a significant investment, and actually more and more investment to actually explore those tools. I guess that's one of the source of sort of anxiety. It is where like I don't know if you guys worked on like front end applications before. So I used to learn like React, which is like a framework developed by Facebook, and it will be the bleeding edge for like a couple of years at least before they like completely change to something different, right? And I think this pace, like every 3 months, it's like completely a different thing, right? I guess like I don't know like what you guys think about that. So.
To say from my experience, I entered college in 1992. And first week of college, some guy in my hall says, don't be a computer scientist. Computers are going to write all the code. Well, got me this far. I'd also say that a time that reminds me of this time is when the internet first became a big thing, like the late 90s. It's just, it's really hard to keep up. Everything was changing. The reality was like, now I can get my pet food online. Now I can, and all these crazy things are going on. And this reminds me of that time. And eventually I did manage to sort of catch up with the flood of new internet stuff. But it's changes really fast right now. It's sort of great, sort of very also scary too.
Okay. I'm a recently graduated PhD student last year. I've been thinking about what it means to do systems projects as a PhD nowadays and how it could work. And I feel like it's actually a very interesting time because tools like Cloud Code allow you to produce ideas extremely quickly. And so you can have an idea, you can validate it so much more quicker than you used to be able as a systems PhD, where you were agonizing about building a particular system over months and you try to get it right. Whereas now you have the ability to really produce all the pieces that you need and then put them together in a way that you like to have. And I think that's an interesting opportunity to just think about the ideas compared to the implementation, what you used to do, and the details of the implementation. At least that's my take on it. But I'm not a PhD right now, so I don't know what the realities are of the work.
Well, I'll just add, I teach a course. Actually, I got to skip it today. Fundamentals of Computer Systems, where you basically start with logical gates and build a microprocessor. And the course interfaces with assembly code. And the students always ask, why are you teaching us assembly code? Nobody programs in assembly code anymore. But I think the value of understanding that really helps you understand a lot of the higher level aspects and issues. And a lot of my colleagues don't teach this class. And when we have folks come in giving computer architecture talks, I can actually follow a good portion of the talk, whereas a lot of them can't. So in some sense, even though these systems are able to do things that we may no longer have to do, it's still good to understand the fundamentals. So even if Claude can do the coding for you, it's still worth spending the time to learn how to do the coding. And I think that's invaluable. You never know when these ideas are going to crop up and help you. Just, I forget, somebody asked, I think Harris, how do you find a good research problem? I don't look for them. I just, read papers and think about ideas, and kind of embarrassed to say, usually some of my best ideas come when I'm in the shower and I'm just, not distracted and just something pops into my head. I don't know where it comes from, but it's slowly piecing things together. And if you were to ask me what my next 10 research projects were, I'd have no idea. I mean, the feeling you have of constantly being stuck and I don't know where to go, I think we all go through that. And it's just, you learn, I'll give it time and something's going to pop in my head again. It's happened before, it'll happen again. Just, be patient and trust your instincts and, do what you think is right and follow your interests and talk to other people. I think that's something that doesn't happen enough in our industry anymore. I feel like conferences used to be places where you could meet your colleagues and talk to them and get ideas from them. And even back then, there were all these publications and you didn't have time to read them all, but you speak to other people and see what they're interested in. And you could either say, well, that's stupid, I don't want to work on that, or that's exciting and I should learn more about that. And, we're all different and we all have different opinions and philosophies. And it's great that ecosystem really makes it an interesting and vibrant place to be. Let it happen naturally is the answer. We watch a video? Yeah.
Oh, come on. Sorry. Oh, I had a question next.
That's okay. You can ask a question.
You touched a little bit on the faculty and teaching aspect. Can you tell me a little bit more about how you has this whole revelation changed the way you think about instruction and grading and testing and so forth? Or is that sort of, we're still working on that part?
I mean, it's always a work in progress. I know, I always assume students are cheating. So, I mean, they're not everyone, but a good portion. So I always make sure to test in an environment where they don't have access to LLMs. I had a conversation with a friend of mine before LLMs came out, and he was talking about how AI is going to revolutionize teaching, where he didn't do well in college because the way they were teaching things didn't fit with his way of thinking. And my response was, well, you didn't learn how, you're supposed to learn how to think. You're supposed to learn how to interact with other people. If you think like it's supposed to be tailored to you, you got it all wrong. And my thinking on that has changed a little bit because now LLMs can regurgitate stuff for you, or if you're confused about something, For instance, I'm learning a lot about quantum computing, and if I don't understand something, rather than having to bother my colleagues or read through the book and get stuck over and over again, I can ask the LLM, why did this work? And it'll explain it to me, and I'll say, oh yeah, now I get it. So there is some change, but you have to be careful not to overuse it and just think, oh, I get it now, because it can always be explained to me. I don't know if that answers. So still work in progress.
Yeah.
In some sense.
I mean, I think fundamentally it's the same issue as plagiarism and cheating, but the problem is now the median has shifted to like just using these tools by default because you're sort of incentivized to use them.
Yeah.
Whereas with the plagiarism, you always had people who were sort of afraid of getting caught and so forth. Now it's just a common case is different.
I think the main concern is someone can explain something to me and I think I understand it. I get it. And then if you ask me to redo it or solve it again or change the problem slightly, I don't get it. And I have to go through the process of really learning it, trying and practicing, and then I'll say I can get it. And I think one danger with LLMs is that everyone's just gonna always think oh yeah, I get it. Oh yeah, I get it. When they don't really. So, and then maybe that's good in a classroom setting, but when you're supposed to be thinking novel thoughts and producing novel things, if you lose that ability to kind of push forward into the dark, there's less movement forward. Sorry, I don't want to, if other people want to speak up, please. I don't want to hog the mic. Do we watch a video?
So yeah, I have a ton of thoughts because as part of my application faculty, I had to write a teaching statement, and when you're process of writing a teaching statement, it seems we're not to talk about LLM at all as part of them. So I think I've seen different approaches to it. I've seen people who decided to completely remove them from the curriculum. I don't necessarily agree that this is the right approach. I think you absolutely need to have LLM as part of what you're teaching because this is this is the future of the field. Now, the key question is how do you create an incentive loop for students to actually learn the material? And I think that this is not necessarily a novel problem. I mean, there are a lot of people who just learn to pass exams. And there are some classes that they are able to get very good grades, even though they don't understand the concepts. This is nothing new. We're just facing similar issues of how do we create the right set of incentive. And I think there are specific things that I've taught as being core problem. One of them is that a lot of the undergrads I interact with are more worried about getting good grades than learning material. So we've kind of had a problem with the shift, and this starts even before they enter undergrads. They spend all of their high school getting really good scores so that they can get to very good university and so forth. So there is a lot of learning to be done in there. And for me, the future of the education we have to give is putting higher weight on the process of learning as opposed to the process of getting good grades. I think, for example, Dan's class that I haven't taken myself, but I've heard through the grapevine, does a very good job at incentivizing to learn as opposed to just getting a good grade, because it's designed in a way that everything builds on top of each other. You really start with the basic, and then it's okay, now that you understand that basic, you can understand this. So if you don't understand it, you can't do well anyway. But yeah, I think it's a major challenge. I think it's an exciting time to be in education, and we will have to figure out the way. But I don't think we should remove them. I don't think we should be gloomy about them. They are incredible tools. Incredible. I've done my webpage within an afternoon thanks to them. I'm so grateful for that already. That's already more than I could have expected.
So I had a quick poll for all the PhD students. if we pass the mic around and you had to ask one or two questions of what would be the most important feedback that you would want to get for your own research or your own career, or what are you most worried about? And you can pose a question to other PhD students or people who have finished and who are in academia, industry, and so on. What would that be? Would this be a good use of time? Like forcing everybody to at least ask a question about what is it that they're going to take away and what will be most useful for you. So,
yeah, one thing for me is how do you stay motivated to work on these networking problems when like academia doesn't really reward it? Like I have lab mates that are applying for academia right now, and I get all like the job posting emails from all these universities, and it's never networking in the call. It's always LLM AI. So how do you stay motivated working on these networking problems when it's not really rewarded?
I can give a bit of an answer to that, which is something I tell a lot of PhD students. Like, you have to love what you're doing. So, like, yeah, you can go work on LLM and ML and get a piece of paper that says you're an expert in it. But, like, if you don't love that, like, you're going to have not a great time. So, I mean, most of the people I know who do networking or network measurement, like, we're kind of weird and geeky about it. Like, it's just like, for me, it's like, it's in my soul. Like, I just couldn't not do this, I guess, as much as it feels like beating my head on a wall sometimes.
I have a question. You said about your career, you can ask a question as well. So as Fabian mentioned that, the systems research is changing fundamentally because now you just have to ideate and probably formulate, and some LLM will figure out all the implementation and such. So that I think is gonna increase the amount of research projects being done. So right now, if you say 3 sitcoms, you can confidently go to faculty market. Probably 3 years from now, 6 sitcoms won't be enough. So my plan, because I'm graduating, my plan was to try to go into academia market after 2-3 years. But I feel like that's a very bad idea. The requirements are going to shift dramatically. The number of papers required to be in the academic market. I know everybody says it's the quality, but I think the quality will still not necessarily go down, but the number of publications to be confidently in the academia market is gonna go way up because of these LLMs. Do you think that's true? And if that's true, then probably I should not delay going into the market,
I mean, yeah, I mean, I get what you're saying, because it looks like all the candidates who come through have these amazing publication records just in terms of counts. I could say, at least at Columbia, we place a lot of stress on the letters of reference. So just having lots of publications doesn't count as much as a good reference. And also, the impact factor of the paper is more important than the count. So someone who has 30 sitcom papers, if the feeling is those didn't really do anything consequential, versus, I shouldn't say 5, one solid paper with a big result makes a big difference. And you do that 2 or 3 times, and that's what gets noticed more than just the numbers. And that's also true for tenure. Before you've gone through it, you worry. I remember thinking, oh, there was 1 year where I had 2 publications. This is not going to look good on my tenure case. And when we evaluate people, nobody ever says, What went wrong in 2022? You look at the whole package. So in that sense, it's a more holistic process, and I would say, don't worry about the bean counting aspect. Do the best you can, and don't try to game the system.
Okay, I can give a slightly different perspective. First is, this is a controversial take, but one of the big challenges in 2021, when I was teaching a networking class and a systems class and a security class across 3 classes, enormous number of people were doing crypto projects. Then crypto crashed. 2022, when I did, there was not a single crypto project. I'm saying, 80% of student projects were crypto projects. Now I'm seeing 80% of, LLM centric, this kind of project. Now, if you look at where specific companies, maybe if I had to cherry pick OpenAI, they actually have to show cash flow positive in the next few years. Otherwise, it's a $1 trillion crash that's coming. Right? Now, if that sequence of what happened in crypto, there's a lot of fundamental advances, but if the economics of AI is actually not going to work through, the whole machinery of like this hype is actually going to come crashing. It's not a matter of will it happen, it's a matter of when it will happen. Right? At some particular point, there is going to be a massive market correction. And when that correction happens, you might actually suddenly see 30,000 submissions from ICML go to 3,000. I would not be surprised, right? But the tools that we have actually built, yes, they will be utilized in a particular way, and it will lead to some changes in the way we do research. Right? So there is a certain short-term thought process to it, and there is going to be a correction factor that's going to come. And we do not know when, but it's actually going to impact how we think about research in a certain long term. So I would not just go by the blind hype that's currently going. Let me pause here because I think what I just said was like quite out there. So I don't want to add to it. Anybody else want to add any thought?
Well, not quite related to your point, maybe to your question on the value of networking PhDs. So I don't know your background or like the exact spectrum of research, networking research you do, but I personally think that we are actually in a very privileged position as networking PhDs because it is very close to industry. So there's a lot of industry positions available technically, and they're still hiring broadly. They just do very bespoke hiring and very targeted hiring, but they do. And second of all, the academic market, compared to what I see with friends, is not as competitive. And it's much easier to find a faculty position right out of your PhD compared to, machine learning, forget machine learning, but even physics or math or anything like that, where the expectation is that you do at least 5 to 6 years of a postdoc afterwards. Whereas here, it seems to be much more common to find a position itself. So I think as a PhD in networking, I'm still very hopeful that no matter what you do, it's going to work out quite reasonably well for you. That's just a thought.
Yeah, keep talking.
It's improvising. Well, I can also, I guess, since I have the microphone, it's true that there might be a market crash, but I think the value of LLMs is here to stay. And it's not going to go anywhere compared to crypto, which it's still trying to find a way to make anything work. But also, and from our perspective, I don't think we do a lot of LLM projects, right? As a networking researcher, at least the thing is, I see at NSDI or SIGCOM, they sometimes have ML applications and they're designed for ML workloads, but we're still working with the fundamentals.
Actually,
Yeah.
if I take Berkeley and MIT as two groups, that is actually changing with the respect to a lot of. If I just take Berkeley, MIT as two groups, I do see a lot of agentic AI playing a big role in how systems are being designed, and also leading to like potentially a series. So Mate is starting a new agentic AI plus systems conference with a paper deadline in a month, right? And as part of my reading, I've added ARDS as like a, and GLIA was a recent paper that came out of MIT, and it's kind of feeding into even, and I have the highest respects for like people like Hari, Jan, who have done phenomenal stuff in networking, but even their groups are also percolating into this thought into how. So your point about using LLMs to design future systems, both of what you and Hasib said is actually quite happening, and even in the paper production phase, right? System design phase to paper production phase, this is actually happening with respect to how grad students are thinking about it, right? So the reason I sort of brought up that crash point was in crypto, it actually hit a lot of people who were doing crypto research very hard, because up until 2021, crypto research was suddenly considered super hot. So suddenly it went to super cold within 1 year transition. So if you might even reach a point where you might be paying 2 cents per query to OpenAI for this kind of risk, and you might reach a point where it is actually very expensive for a PhD student to be using these kind of tools to actually make. And so there is going to be some notion of economic equilibrium that will hit, where we will be using these tools, but will also be, what that equilibrium point is, I don't know yet. But these tools definitely are going to be useful, are going to be used. They are going to be part of the flow. That I don't think we're going back on that front. But is that going to doom us? I don't think so. But what is really going to doom us is when there is a crash, there's going to be a significant market correction about what is important.
Yeah, that makes sense. For me, it was mostly the perspective as a PhD that wants to build something. For me, if you have an LLM at your hands, it's so powerful in the sense of you can execute an idea so quickly, and then you can validate it. It doesn't mean that the LLM is going to be part of your paper submission, but it's going to be part in the execution of building whatever you wanted to prove or what it wanted to show. And I think that can accelerate the process in how we do research in quite a lot of ways. I remember myself, I agree that it's important to understand what you do, but I remember just myself spending months on just stupid, low-level systems issues that I had to learn myself, which I don't know if I actually did take away a lot of lessons from it in terms of the way I think about systems, but they just had to be done. And if I could just execute the idea quickly by just generating the code necessary for it, it would get me to the point of my publication much simpler, much quicker. Now, whether that's related to a market crash, they could increase the cost, but I think that's a different topic.
So just on the coding part, I completely agree with your point, but just to give you a counterpoint, Scott Clemmer published a paper in 2008, 18 years ago, on example-based programming, right? And he exactly showed how you can actually use large repositories like GitHub to get snippets of code. What has actually happened in this 18-year time window is It has been made into a beautiful prompt that generates a beautiful functional code. What he did was kind of ugly, give you only patches of code. And he even did a case study where he hired 120 Adobe engineers and showed, 200%, 300% improvement in his Sky paper. But it never became mainstream, but now it's suddenly becoming mainstream. So if you actually thought this is actually a new paradigm, it was done 18 years ago. And his student actually tried to commercialize this as a startup, and it kind of went midway, got acquired, and then kind of stopped. It did not go too far, but now we are actually reaching a point where that tool now is looking suddenly super sexy.
My perspective, I'll reiterate what Felipe said, which is you have to love what you do. And if you're trying to game where things are going to go, you risk picking the wrong trajectory and, the rug being pulled out from under your feet. When I look at, one thing to do is to look at what's getting published and just ask yourself, what are the themes that are kind of coming through? Like one of them is satellite networking. That was non-existent. Obviously it's inspired by Starlink, but a lot of times I see those papers and those are examples of things where I say, oh, I didn't know that was an interesting thing to look at. Like the orbits, I never would have thought to kind of frame the problem in terms of how the satellites move or don't move or, put them at different altitudes. You get all different sorts of network behaviors. Lost my train of thought. Anyways, so to me, that's an interesting upcoming area. Something that I worked on in the past that nobody ever seemed interested in when I was working on it was resilient networking. So how do you handle cases where the main internet goes down? We proposed this as a large NSF proposal back in 2002. And the response was, who cares? Like the internet never goes down. And, there's papers even in NINES about resilience. Think old ideas recycle and become relevant again. All what you think is interesting.
It just brings up another sort of asking a question the other way around, and that is, what are examples we can point out that research community missed over the last couple of years? So, what comes to mind immediately is the emergence of social network platforms. There should have been research in place that would have directed these platforms away from the misuse. That would be sort of an obvious thing that there was not much research in that domain, I guess. Trying to indicate what is the possible misuse of social networks when they came along.
I think you can apply that argument to
If you use that argument to your own previous argument on security, people are going to be producing massive amounts of code with massive amounts of bugs. Right now, that the checking of what is being produced is actually quite poor. So I think cybersecurity of what is being provided is actually going to be a huge problem. And it's going to potentially be the kind of examples where, these tools are wiping away hard disks and, is sharing a lot of information leading to privacy violations.
But at least there has always been research arguing for the social network context. And these social networks came along in the late 90s. There was not much research that pointed out here is something that we really should prevent these networks, these social networks from.
But I don't think we can just quite control that because having worked in startups, the way many of these, especially if a young kid wants to launch a startup, they just pick something They pick a bunch of tools, they get a bunch of traction, and it becomes big. TikTok, for example, nobody saw it coming in a very big way, but it has changed how people look at tiny videos, and it has actually it's both interesting, and it has also created significant social changes on how people interact. One funny story about TikTok, there are stories in taxi drivers in India who spend the entire day just sitting in their taxi, relaxing, watching TikTok videos for the entire day, and then just drive back home. And the joy people get, it puts them in a different state of mind, and they don't even care about their own jobs. There've been some studies about them as well. So.
Happens to professors too. I mean, I get on Facebook and they start showing me Sopranos clips, and before I know it, I'm Google asking, who did Tony whack and whatever. Anyway,
you can know when that happens based on the conversation the morning after with you.
Oh yeah.
You reference the Sopranos, we know you've gotten lost in the algorithm again.
Right, Sopranos, Game of Thrones. Yeah, my Facebook feed knows exactly what I'm interested in. I was going to say something that the research community missed. Which we then sort of followed on after the fact. First of all, peer-to-peer came out of Napster, right? And then we jumped on that bandwagon. Everybody had ideas about peer-to-peer. And then Bram Cohen came out with BitTorrent 6 years later. And then that was another paradigm shift. And I feel like, I just remember thinking, why didn't any of us come up with this? It was just like sitting there waiting to be grabbed. And then I don't know if the research community missed it, but I felt like it took me a while to understand the value of certain things. So I remember we were doing peer-to-peer, and then cloud computing came along, and I said, this is just client server, like what's new? And it took a while to understand the difference between what the cloud represents and what the old formalism of client server was. So I've, just certainly a history of missed opportunities, I suppose. Or we latched on after the fact, but why didn't we come up with this? Why did some kid in his basement room beat us to it? But sometimes that's how innovation happens. So
I think the worst thing that could happen is
that one of those missed idea ends up being a rejected paper, right? Like that. I think that's really what we want to avoid as much as possible. I think NINES is addressing some of that. That sometimes there are ideas that deserves to be out there. They might not have the level of evaluation we anticipate in some system conference, but they still deserve to be out there because they're important. And I don't know if we have great safeguarding against that. I mean, archive is one thing. But it's very hard to know what from archive I should be reading out of the 10,000s of submissions. So yeah, as a whole, I think there is a need to rethink about the model around what it means for something to be out there. There were mention of blog posts. Maybe blog posts are another way to put ideas out there so that they get some reaction from people. I really don't want us end up in a situation where someone has thought about, for example, ethical consideration or and just one other thing I wanted to mention is one thing that we haven't really valued enough sometimes is the limitation and the potential ethical concern. I mean, right now, I know some conferences have like a requirement of having an ethics statement, but oftentimes it feels like the ethics statement is like this work brings no ethical concern, partially because there's no space in the main body, or there are tons of reasons why you don't want to invest too much time talking about your limitation or your ethical concern. But having as the author like this real deep thinking about what could come out of the system that I'm enabling would be really helpful. And if we create a more welcoming ecosystem of like, oh, you found all those limitations yourself and you put them up front, I think ultimately we have a better scientific process. Right now, I feel like sometimes I'm giving the stick that I'm gonna get punished with.
So again, I mean, I don't know how to make this change, but before we had such easy online networking, people used to talk to each other more. And I think really that is the best way to filter out ideas. You know, I used to have this joke that you know, you go to a conference and people would ask me if I read any of the papers, and I said, no, I'll go to the talk. I don't have to read the paper. And I wouldn't even go to the talk. I'd just hang out outside, and then people would come out and I would ask, like, were any of the talks good? And they'd say no. So I'd say, yeah, hey, I just saved a whole bunch of time. But you know, I think the human interaction, you talk to a colleague, this is good, this I didn't like this, here's what I did like about it, here's what I didn't like about it. I always try to encourage my students to talk to each other more, try to create opportunities for them to do so. They seem resistant. When I was a grad student, every day we all came into the lab and spent a bunch of time schmoozing and talking about the field. I feel like this doesn't happen as much now as it used to, at least not at Columbia. So I wish I could encourage you guys on how to do that more. I think that's a good way to do this filtering that you're talking about what do I read? What should I look at? And just one other point, I think students have a better eye to what's up and coming than faculty. You know, I'm aging and I'm sort of losing, you know, like I can't tell my kids what music is hot. And I feel the same thing about hot topics. Like, you guys should be driving that. You should find what interests you and convince each other what's important and what's not.
I would generally agree. I think from, you know, just, I guess from anecdotal experience, you know, talking to you know, other graduate students in the lab, just learning about the projects that they're working on, seeing how they do research, how they think about research, how they ask questions. I think that having that human interaction, you know, in the age of, you know, AI and bots, I think having that real kind of human interaction and, you know, just really getting a feel for the people around you and getting that feedback, I think that's incredibly valuable. So I wanted to say I generally agree with that. Yeah.
Do we watch a video?
No. All right. Okay. Well, I'm glad people find some value. Yeah.
I'm not sure if I'm getting ahead of myself, but this is like more of a teaching question, going back to the topic of LMs and Gen AI. So I'm TAing for a project-based course, and students submit their project proposals, and there's one submission that's like so obviously AI because the subheading says, here are the questions you should answer. So it like they didn't even bother to paraphrase, but it is also more of a like, I think I don't want to be, I guess, pessimistic, but it felt more so like it seems like everyone is using AI more or less, but it's just who is better at masking that, or who is better at paraphrasing, who's better at hiding the fact that, and it's not that Gen AI should be like, it is a great editing tool, for example, but I just wonder, how do you approach a situation like that? Because you do want the students to, this is a project-based course, you don't want the students to do a project that they're not even excited about. So I was wondering, I'm not grading it yet, but as like educators, how would you approach that?
So across all my courses, I blindly say you can use whatever tools you want. So I do not pose any restrictions. And I've also canceled this notion of having an exam. So across none of my courses, and this might be a controversial take, but I've stopped using exams. What I do instead is I tell them that you can use whatever tools you want, but whenever you answer a question, you have to write it in your own words. And if I actually see that you're not writing in your own words, and if it is obvious that I can make as a human being that it's not, then I will hold you to it. It's not about reducing points or actually calling it a zero, but publicly saying, this is what you presented. in front of the class saying, this is not, this kind of question answering is. So once somebody is on a spot and they realize that that's something that's actually not going to be helpful, that human behavior actually changes. Two, I also remove the fear of grading. So to get a decent grade in a class is not about anybody given infinite time can learn any subject, right? It's mostly about that discipline of just coming to class, doing your required set of things. So I actually give a regular amounts of homework for every reading, 2 questions, 3 questions, and get them to, but really giving them a lot more regularized work and making sure that they are actually on top of this. And going back to school systems, schools actually do a better job than colleges, I feel. With specific regularized testing, they're actually keeping middle school, high school students a lot more accountable in the process. Like, for example, there's a school called Stuyvesant right nearby, right? And a lot of people are trying for Stuyvesant, and I know a lot of kids going through Stuyvesant. The effort that an average Stuyvesant student puts at learning during Stuyvesant, I fear is actually way higher than the same Stuyvesant student going to MIT or Stanford and studying during their college years at MIT or Stanford. The culture, I don't know whether you agree with that.
I went to Stuyvesant and I went to MIT. So
no, but I mean, I'm actually, when I see students going through college years, the rigor that they went through in high school, I feel is kind of dropping. At least I see this in NYU as I'm not saying with respect, I see Stuyvesant students separately. I also see NYU students, then there is a subset, but I do see a pattern where there is a significant drop.
Well, I was drunk a lot more at MIT than I was at Stuyvesant. I can assure you of that. But I mean, different age group, different learning paradigm, right? I mean, high school is more regimented. I like the MIT model of the fire hose. They throw everything at you so fast, there's no way you can keep up, and you just struggle to keep up as best you can, and you learn a lot that way. And I guess to your question, over time I've grown to hate grading and exams. I mean, they're a necessary evil in some sense. And I remember being a student and only taking a class because I had to take it, and only caring about a topic because I had to care about it. And now I never have to take a class. I never get graded on anything, and I just want to learn stuff. But I can remember when I didn't think that way, and I just thought I have to hit these marks. And I feel bad. I know there's students in my class who couldn't care less. Maybe they get lucky on an exam and do well when they shouldn't have, or maybe they really understood the material but they bombed an exam. My opinion on that is just it all works out in the end. The ones who got lucky, they won't go as far as the ones who understood and maybe got knocked back a few steps. So it's a never-ending journey, so to speak. Grading is just the best thing I can do. I have a class of 200 students. I can't sit down with each of them and let's see what you really know. So, but in terms of like if they cheat, the meta answer is you're only hurting yourself.
And for the record, today was actually a teaching day for me. I canceled my class and forced my entire class to come here. And I got an attendance of 10 out of 15. And I call that a success. 10 actually physically showed up here, and 5 are at least supposed to join online. I don't know whether they did, but.
How many of the 10 stuck around?
Right now, 0, which is why but they stay.
The hours they were supposed to.
Yes, I said minimum of 2 hours, so many of them stayed for 4.
That's a win.
Yeah. I think there a big challenge, especially with with education at a college level is how do we effectively evaluate the students, especially with the rise of AI and, cheating and, all of that. And it's tough to evaluate them, especially for earlier classes. How do we evaluate them at scale? Because a lecture could consist of hundreds of students, and it's a lot of work to grade those. I think, I don't claim to have, and I don't claim to have the answer for it, but a idea that I'd like to at least throw out there is, for more project-based courses, especially, junior and senior level or even graduate level. In my experience, I've had professors where actually they gave presentations or oral exams where you have to go and sit in front of somebody and explain the work that you did and explain your reasoning and your thought process. There are a number of issues with that, of course, scale being one of them. It's tough to have, even just a 10-minute session with 100 students or 50 students in a class, that would take more than an entire lecture period. There are problems with, if somebody has English as a second language, but I think the idea of shifting away from maybe tests or kind of more, I want to say more like regimented or standardized evaluations to, especially at these senior level classes, more evaluating the students' thought process and how they went about it. Not only will incentivize them to deeply learn the material and really invest in their education and their work, but it also may ultimately help with the actual evaluation itself.
So you're going to be looking forward to your qualifying exam, your thesis defense.
But that's the qualifying exam. Okay. But I think that, that's part of the process. You have to, for a PhD, of course, you're going to go and explain your work and present your results. But ultimately, I think it's beneficial to get comfortable explaining your thought process and your methodology.
Agree. Yeah, I mean, like the scalability problem is always, something that is in the back of everybody's mind when you're thinking about having an oral presentation. As a professor or as a teacher, how can you stay concentrated when you have more than an hour of presentation of like different students in different groups and so forth? It's very hard. In a way, also the fact that LLM allows some of those tasks to be offloaded means that we like there is an opportunity to kind of change the way class are being taught. So as a TA, I'm pretty sure everyone in this room who's TA'd recently has realized that students don't come to office hours anymore. These hours are dead. So like that's time that we can use to do other stuff. One of those stuff can be, having recitation, where the TA is assigned a certain number of students who have to come and explain, for example, homework they do. I think that's what you do then, kind of in essence, my understanding. But like that's one way of using the opportunity enabled by LLM to change a bit the paradigm of how we are training and verifying the competency of the students. As a whole, I think there are a lot of other things like this that are feasible. Maybe, like, for example, during one thing I liked about the pandemic is the fact that all the classes were recorded. So I like the hour of classes we had on Zoom were actually an opportunity to ask very specific questions about the material. I think maybe, like these kind of approach are something that we should pursue, and they will enable then to have more ways of verifying knowledge of the student and so forth. I just think it's about being creative about the way we teach and we verify that students learn. And you mentioned grading as being like the worst part of the work. I agree, and I don't know if we really need to grade. Maybe this is an outrageous opinion. I don't think we should have grades. I think you should pass or not pass.
It's too great. It's just Peter.
Yeah, maybe, but I think if you like know the material, you should pass, and then the grading, like right now, it provides the wrong incentives. Students want to get the best grade, and sometimes it means using an LLM blindly.
Well, I'll just say quickly on that, when we have undergrads who want to work with us, I mean, it certainly doesn't hurt to check their transcript and see if they're a C student or if they're an A student. You know, it tells you something. So while I agree the grades are, you know, they're not accurate indicators. Someone who has a 3.9 is not necessarily better than someone who has a 3.87, but someone who has a 3.87 is probably more productive and effective than someone who has a 2.3. And that's not always the case, but generally it is a rough indicator.
So, I mean, I'm happy to even put this publicly, but the way I grade is if anybody shows up to my class, pretty much does all that is required for a class, they get an A. If they are short on a few things here and there, they might slip to an A minus. If they don't show up to the class regularly, they are potentially they might be touching B plus, and but generally I do not go below a B plus or a B.
This is a grad class.
Grad class, even to some degree, undergrad classes have not gone below a B. And if I'm actually trying to give somebody a C, I'm trying to follow up with them like crazy, trying to make sure that they don't fail the course. So I look for indicators of people who don't show up, who don't submit, and I'm like begging them to get to some basic passing grade, because especially for international students and so on, what people don't realize is if they get one fail grade, the relative implication on the visa process is ridiculous in this country, that as a teacher, you have to be kind of cognizant on, even if they're not thinking through the whole process, we as professors sometimes have to think through that whole process to make sure that, you know, because of your class, they're not affected. And I try my level best to keep I don't get into personal the things of, you know, why somebody is not doing well or so on, and refer them to any help centers if they really need. But at a high level, this is the blind way I grade, and generally I don't even give a C. So if somebody has taken my class and somebody got a C, then typically they did not even show up, they did not do anything for a class, and I had to beg them to make sure that they passed the class.
So we're actually almost out of time. Andy, is Kiran available? Oh, there you are. So let's take like a 2-minute break, 3-minute break, and Jane Street is going to do a little presentation for us, and that'll end the day for us. That'll end the technical portion of the day, I should say. We still have our social hour.
So are all the PhD students guaranteed a job?
Oh, yeah.
Okay. Especially if they stayed till the end, right? They now need to deserve a job, right?
Come with me afterwards. We'll find you your desks.
I should add, this was not a requirement by Jane Street that, you know, it's not like one of these timeshare things where you go up, you get free breakfast, and then you have to listen to their pitch. This was, you know, hopefully everyone will be really interested in finding out what Jane Street is doing with respect to networking. So, and it was not part of the initial deal. Just we decided to conclude this.
We should be very thankful to Jane Street for, you know, doing this whole. It would not have been possible without all your help. So, thank you very, very much.
Sorry, do you say we're taking a break? I don't want to.
Oh, do you leave like a 2-minute break, or do we just roll into it? Okay.
Right.
I hope Andy's going after this because I'm effectively an intern, so I hope someone else is doing closing address. But yeah, thank you all for joining. It's been, and thank you for Andy and Dan for very graciously organizing this pod. I've had a lot of exciting paper presentations as well as riveting discussions, and so excited to see that next year onwards. So anyway, I'm Nira. I'm a visiting researcher here, and I have the privilege of telling you a little bit about what it's like to be a recovering academic in the financial industry, as well as especially at Jane Street. So it was 2 a.m. and I had to pick a theme for my talk, and so I'm going to tell you a little bit, just share a little bit of perspective about how sort of research culture, like intellectual culture at Jane Street, I find is different from academia or hyperscalers where you may have that I have worked before. And so let me start with a quick pitch for the visiting researcher program. So I'm going to give you the N+1 version, but if you are so inclined and you find you're sort of piqued by what you hear today, you should go talk to Nate Foster, who is now a professor at EPFL. He has been sort of part of this program for a while, and I think he can give you a much more refined perspective. So anyway, so I recently completed my PhD from Carnegie Mellon this past fall. I'm a networking person, and my interests are broadly at the intersection of systems and analytical modeling. In the fall, I'll start as an assistant professor in the computer science department at Stanford. But until then, I'm full-time on the ultra-low latency or ULL hardware team. And so if you're familiar with the HardCamel language, this is an embedded DSL that Jane Street has been sort of evangelizing for hardware design for a long time. It's a dialect of OCaml, so it takes a little bit of getting used to. But this is the thing that underpins all of our trading systems. So the hardware is designed via OCaml, via HardCaml, and ULL is the team that's responsible for developing the language, maintaining the libraries, and actually implementing the hardware systems. So okay, so what's the program about? Well, the opportunity is really to work on these ambitious long-haul research projects while being embedded on a team like ULL or in Nate's case, networking, and working sort of on a team which is basically touching these high-value financial systems, right? You're sort of trading billions of dollars every day. And it's a sort of unique insight into what is otherwise a tight-lipped and highly regulated industry. So I'll talk a little bit about sort of what that means in terms of what research actually looks like at Jane Street. So it's not, there is an academic component, but there's also sort of more like a primitive version of research. Okay, so what the hell do I mean by convenience stats? And so I think the best way to exemplify this is we're going to play a game of Never Have I Ever. I'm told there's alcohol somewhere, but we'll play the PG-13 version of this, which is I'm gonna ask you a series of questions.
Maybe we should go to the social event then.
Yeah, that's not a bad idea. So I'm gonna ask you, a couple of questions, and if you hear a thing where you haven't done the thing, you can put your hand down. But we're gonna start with the hands up, right? So have you raise your hand if you've ever written an application which uses Linux, standard Linux setup? And your hand's got to be up.
Oh, I never.
Yeah.
Never.
Okay, so you've all done this, right? You've all written an application which uses Linux TCP sockets, right? How many of you have decided that this is actually too slow and moved on to IO Uring? Or some flavor of this, right? You've some mix of kernel and user space network, right? And then at some point you decide that actually kernel networking is too slow, and then you switch to DPDK plus some maybe user space TCP fiber. How many of you decided that that was actually all too slow and then re-implemented the entire TCP stack from scratch, right? And I'm talking everything, right? Congestion control, flow control, reassembly, all of that. Wow, you guys are really hardcore. Okay. How about redesigned your NIC from scratch to better support this?
Okay, that's great. I was preparing for, just in case like March was showed up. I had one more, which is buying and dissecting every possible L1 switch on the market. Okay, so we're zero hands right now, right? And so if you might be and so for reference, like this is where my paper evaluation efforts usually end. Right? We get to DPDK, we have this application that operates at 100 gigabits per second, and we sort of call it a day because that's good enough. But if you're like an academic and you're looking at this sort of list, you're wondering like why the hell would anyone bother going down all the way down this list, right? Every sort of rung in this ladder represents like an astounding amount of effort in terms of people hours, energy, and if you're like an engineering company, costs, right? So this is what I'm talking about when I say the convenience tax, right? To break sort of these abstractions, you're paying a significant cost. And often it's actually not worth it because you might think that there's actually diminishing returns once you get to like re-implementing your deck or like understanding exactly how an L1 switch works. So, but in the sort of the context of Gene Street, this is where revenue lives and dies, right? So you have basically value that you're deriving from like every single rung over here. And I'm really not joking when I say when I talk about some of these things. For example, Ron has a blog post that he publishes every year about what the interns did that summer, and just one of these things was like re-implementing TCP, the TCP stack in OCaml. So there is sort of, and this is like an intern project, so you can imagine what sort of would happen. So at this point, you might be asking, how is this different from other industry efforts, right? So if you worked in industry for a bit, like doing this sort of large-scale engineering and fine-tuning is part of the process of building a performance stack. And we've seen this, right? So for example, like Microsoft has made invasive changes to the networking stack in order to get like IO kernels and Arrakis. Similarly with Google, they have this like new hardware transport protocol, which they published at NSCI last year. And so there's all this like grand effort on the hyperscaler side. The problem, or rather the difference, is that the hyperscalers are really optimizing for efficiency, not for raw performance. And the reason for this is that deploying new tech only really makes sense if, after accounting for like R&D costs, those total cost of ownership, deployment effort across the entire fleet, and all of that, dollar for dollar, you're making more money than you were previously making, right? So that is the incentive to build something deploy something which gives you better performance. In the finance world, you might actually get disproportionately higher returns from a trading strategy that hinges on like a 1 nanosecond latency improvement, or discovering some piece of information about how a switch works, or how a trading system or how an exchange server works, which your competitor doesn't know, right? So you're deriving like significant value. You don't actually know a priori what the value of this thing is. And so it actually makes sense to invest what seems like profligate amounts of time and effort, because the payoff can be more than you imagine. And so sort of the TLDR here is that financial markets are zero sum. And so if you're not investing sort of the commensurate amount of time and effort into doing things, and your competitors are, you're probably going to go out of business. And so I will sort of contend that the profit for Jane Street and other trading firms is really in this bottom segment, where like you're sort of pushing all the way to make profit. And this is actually good news for if you're a sort of interested in first principles clean slate research, because the one thing that both of these sort of actors agree on is that money is no object, right? So if you're interested in building things from scratch and sort of like taping out a new chip, or building a new ASIC flow, whatever, that works if you have the resources to do it. And so that is sort of the culture that Jane Street embodies, and so they're willing to push all the way to derive value. Okay, so this is not a very technical talk, but I'm going to give you sort of a whirlwind tour of the different research directions that I'm looking at on the ULL team, as well as sort of networking more broadly. So I'm going to talk a little bit about what characterizing the financial the traffic that we see in Jane Street networks, what sort of clean slate network hardware redesign would look like, and dealing with uncertainty in clock synchronization, which we've heard a little bit about that today, and I'll tell you like what we've been thinking about. Okay, so you're probably all familiar with this paper from like Theo Benson, Aditya Kela, and David Maltz. This was a paper that was published in IMC in 2010, which was basically talking about characterizing the data center traffic in the wild. Right, so they looked at this like broad cross section of 10 data centers across universities, enterprises, and cloud providers, and they basically just published reports about like what the topology looks like, what the server count was, what the oversubscription ratios were, and also like some really useful details about the distribution of concurrent flow counts or the link utilization. Right, and so these graphs are how we know, for example, that the median link utilization across like data centers is less than 25%. Right, so this was back in 2010, but these were sort of the core empirics that were driving how we design data centers back in the day, and continuing to do so today. Right, so every year we have like new works which are sort of updating these results in modern contexts. So in a hyperscaler context, the methodology looks something like this, right? So you're basically doing like packet subsampling at a few different vantage points in the network. And basically what you're doing here is sort of assuming homogeneity, right? So you have this very nice factory or some sort of flow network. And by subsampling at like a few different tiers, you're going to see like roughly what the distribution looks like across the entire data set. So you're sort of leveraging the homogeneity that you know exists. And you might do some sort of coarse-grained SMP link stack collection. And the point here is that you really only care about steady state. And so you're okay with collecting measurements at the granularity of like 1, 5, 10, 30 minutes, whatever. But things actually look very different as far as a financial network goes. So, for example, topologies and links are not nearly as homogeneous. And so there was actually Andy had a paper about this, like I think it was called NINES'24, where they were basically sort of unveiling the curtain on what the financial network topologies might look like. And the other big problem is that the events that we really care about, so for example, like microbursts and sort of the bursts that we see due to multicast, so like buffering in switches will you can handle only so much buffering, and then once you have sort of tail drops at the input, you're going to see either packet retransmissions or like you just basically have more egress. You have more packets that you're trying to send on the egress side, which you necessary. So these are the events that you really want to capture, but the granularity at which they happen are way more way finer than what you would get with like traditional polling switch counters and so on. And so there are sort of these challenges about like what does the methodology need to look like in order to make this tenable for financial networks. And so yes, this is the paper that I was talking about where like Andy, Brian, and Nate, and they were talking about sort of like what the design considerations for the internal Jane Street trading systems, like what would it take to sort of, if you were to deploy this with, for example, L1 switches, or versus moving this in the cloud, versus moving this to the cloud. Okay, so yeah, so we've been sort of thinking about what it means to be able to collect the data that we need in order to make judgments about what switches to buy or building our own switch. The other question that I've been sort of really interested in as part of the ULL team is it's very simple, right? So given infinite resources, how would you design network hardware that achieves like the minimum possible latency while optimizing for multicast? And the second point is really important because the commodity switches that you would buy from Arista or like any of the switch vendors today, they really don't give you any guarantees about multicast, right? And that is like specifically the scenario that we care about. So for example, if you look at, I guess what was state of the art NVIDIA switches years ago, you have 32 400 gigabit ports. So that's 12.8 terabit per second of bisection bandwidth. And these are transceivers that are basically designed for throughput, right? And they have deep buffers, they have deep pipelining, and they also give zero performance guarantees for multicast. But if you look at what kind of workloads that we would see in a switch at Jane Street, you might see a pattern that looks like this, right? So you have sort of this port, which is bursting multicast traffic to all of these egress ports, and then you have some like other sort of distribution from the input to the output, right? And so what does it take to build from scratch a switch backplane which is designed for low latency multicast? And this is a little bit of like a mischaracterization in the sense that this is actually really a spectrum. There are sort of intermediate design points where we have switches that are explicitly designed for low latency trading. But again, the point is that if we're willing to pay the convenience tax and go all the way, what would the hardware actually look like? And the final problem is is looking at clock synchronization. And this turns out to be really important in the context of the trading systems that we have today, because you want fine-grained timestamps which you can rely on, right? So the problem, I won't repeat this because we've sort of seen a talk on this, but you basically have these two clocks which are running at different frequencies and have different offsets, and you're basically trying to establish some total order over the events that are being generated by the respective processes. Right? So I want to sort of merge them together in a way that in terms of if I had a global clock, this is what the event order would look like. And the norm in the industry today is to pay time as a service vendors for fine-grained, like nanosecond scale clock resolution, right? And this is actually fine because you're getting nanosecond precision, and that is sort of the granularity at which your trading systems are operating. But again, like this is a service that we're paying for, and we may actually be able to do better if we just sort of build this functionality in-house. And so again, the question is, if we're willing to pay this convenience tax, what can we do? So here, there are a couple of like interesting research questions, like if we are trying to mix clock sync protocols that do and don't need hardware support, how do we sort of interpolate between them? Right? So you might have some protocols where you explicitly need synchronous Ethernet, special optics, and so on and so forth. Whereas like some maybe, you might be okay, you might be able to get away with just software support. And secondly, timestamps have this inherent uncertainty. So how do we still reliably compare them? And so here, so this is work that I'm interested in. And so Steve from NYU here had a paper a couple of years ago, which was looking at this notion of like probabilistic fair ordering, right? So if you have timestamps with some amount of uncertainty, you may be able to build a distribution around that uncertainty and compare them in a probabilistic way instead of just sort of taking the timestamps at face value. So there was sort of a whirlwind tour of like all of the things that we're thinking about on ULL and networking, and we're sort of happy to talk about this. Like it's you have to be sort of careful about how many details are shared and so on and so forth. But generally, that is the gist of the problems that we're facing. So anyway, it's a wonderful sort of research culture, both in an academic sense, like they're publishing papers. They have visiting researchers from academia who are embedded in the teams. But also, they're trying to like reverse engineer like what the hell this black box exchange is doing. Right? So that is like in a very primitive sense, like what research is, right? You have sort of this, you're trying to discover some reality about the system that you're with. So Anyway, so that's the end of my talk, and I'm happy to take questions.
Thanks for a really interesting talk. And a very good.
Okay, yeah. So you mentioned that the topology was different. Is it unknown to you as well, or is it trade secrets that you don't want to share? Is it which of those two is
Yeah,
it?
so I think at this point, so let me sort of preface my answer by saying that the paper that Andy wrote 2 years ago, this was sort of it was like a pioneering effort, right? Like no one in the finance industry has done that before, and precisely because these are all like very sensitive. Like if you can sort of figure out like what topology your competitor is using, you might be able to tell something about like what sort of latencies they might observe and so on and so forth. And so I think the short answer is that it is like internally this is known, but it's in this sort of nebulous realm of like how much can we talk about without giving too much away. And so I think I imagine there will be more papers in that line, but that's about as much. That's about as much I can say at the moment.
Great. Well, thanks. That makes sense.
Follow up. So, in terms of the traffic characterization, so what can you say? How different it is, or how much the same as your usual data center traffic?
Yeah, I mean, so a lot of that is an artifact of the topology, right? So, for example, the paper that so the paper that I was talking about here, they have stats on what is the I think the average or the median like statistics about like what the frame size would receive from the exchanges. And this is sort of it's not saying anything about like the network in particular. It's just saying like, oh, this is what like a market broadcast would look like, right? And so internally there might be other processes which are like using that data and sort of turning it and then producing new feeds and so on and so forth. But it's telling you a little bit about like what we see from the perspective of a trading system receiving data from an exchange. So yeah, I think there are like part of the challenge is that any statistics that, for example, like Andy would tell you are predicated on the systems that we have built, right? And so like if you had sort of built your system differently, you might see different characteristics. And this is somewhat different from a traditional data center where like it's a customer who is sort of sending packets. And so you are like a blind observer to what's happening. You're sort of incidental to the traffic that is flowing. All you have to do is collect a couple of link stats. Whereas here we have the ability to like design systems and use or like produce new data.
But I mean, let's say you still run TCP, for example. So you have flows, for example, that makes up the traffic.
Yeah. So one thing they say in the paper, for example, is like TCP is a fraction of like the data that we see, right? Because feeds that you would get from the exchange are multi-cast.
Yeah.
And so like that already tells you something about the protocol's use. Thank you.
I'll have a little bit research-wise question. Like, what do you think about the end host space here? For example, like you check out most of the stuff in terms of the end host, like cutting down the latency from, I don't know, a couple of like 2-digit microsecond, the single-digit microsecond, even like it's a lot saturated. Nowadays it's very difficult to create a system where you can like beat the hardware limit. My understanding is that most of these companies, I was having some experience interviewing with a couple of other competitors, they're either using the like solar flare type of NICs or like some system on the chips, FPGA, that type of stuff. Like regarding the software, do you think still there is a place for innovation, like I don't know, like some novel protocol or that type of stuff. What do you think about like research-wise here, not about engineering?
So I think Andy can correct me if I'm wrong, but I mean even at a trading firm, like you will have a spectrum of time granularities at which you care about, right? So there will be some systems. So for example, if you're trading sort of long horizon options or like just not very short-term speculative trading, you really don't care too much about gains. Like you're more worried about, for example, in that case, you might have a lot of data that you need to collect, and so internally your network has to support like 100 gig, right? So in that case, you might be optimizing for throughput and latency. And so I think there is a spectrum, and I think end-host networking has like a role to play somewhere in there. But in the context of like ultra low latency, you know, I think it's not a stretch to say that like if you hit the keys, you want to follow.
Okay, thank you.
Just another quick question. How far do you think we are from like the optimal? You know, we have squeezed everything.
Yeah, that's a good question, right? So I think I mean, and there's a there are like multiple sort of layers of components that you're dealing with, right? So you have your L1 switches, which are basically just doing sort of pure electrical switching. You have your like commodity switches, which are actually doing using like MAC and IP addresses and all of that. And then you have your NICs, which are like sort of receiving the data, processing it, sending it up to software if necessary. And so I think, generally speaking, there has been like a very concerted effort towards like piecemeal optimizing each of these things. And you really fundamentally just have to do that to be competitive like at a trading firm, right? Like if you're doing ULL, like you can be sure that like other firms are also doing similar things. And so the fact that Green City is making money gives me some confidence to say like, oh, they're going pretty good. But I think how far we are off from like fundamental, physical speed of light limits. That is hard to see, right? I think, and part of the calculus is like you have latencies which are imposed by transceivers, right? Your choice of SFP is going to affect what sort of latency characteristics you see. And so there's a lot of these different components which you have to account for and like think very carefully about. And so, we would presumably buy the best hardware that you can find like on the market, but that is unless we go in and sort of design our own transceivers that PHYs from scratch, then it's hard to say like how far. Yeah. But it's an answer.
I have another question. Maybe again, you may not be able to answer that, but so I remember I paid a little attention some, I don't know, 10 years ago. So there were these companies that were digging new fiber between New York and Chicago to get the latency gain over the existing ones. And then there were these microwave connections or whatever they use. Is that all part of the network topology, or is that?
I think so. I'll also defer to Andy on that because I actually don't know. I don't know offhand.
Oh, I mean, maybe simplifying the question. So, do you sort of use additional, connections beyond sort of
like wired
public internet infrastructure or something like that?
Yeah. One thing that's really interesting I found about the financial networks is that very little of it goes over the internet. We're going to peer with, exchanges privately. So for a network of our size, we probably have a lot of different peering points compared to, what you might expect. And yeah, many exotic link types.
I have just clarification on, you're dealing with these clock skews, and also you're interfacing with the exchanges. Are they providing very highly accurate, high-speed interfaces, and your issues are how to deal with stuff in Jane Street, or you're trying to deal with rectifying something that's behind the curtain?
Yeah, that's a good question, right? So I think, I mean, as far as like latitude and agency goes, we have sort of complete control over the Jane Street network, and so you would sort of imagine that most of the gains in terms of latency or like whatever design you could do would be on the Jane Street side. And so indeed, right? So for example, in the context of clock sync, the generated timestamps are like in the Jane Street domain. And so like how we generate them, how we sort of do packet timestamping, how we use those timestamps, like that is all sort of part of the design process. But so to answer, to the other point about sort of rectifying what the exchanges might be doing, I will say it's less about rectifying and more about exploiting, right? And so again, you can imagine like firms have very little incentive to let the exchange know that there is async, right? A much better strategy would be to exploit that async. And so again, right, like, so for example, if you know the internals of like what the exchange network looks like, which we don't, you could presumably gain an edge over your competitor. So part of this sort of primal research effort is to sort of like reverse engineer this black box and see how best to get this edge.
But the heterogeneity is on the Jane Street side, or it's on the exchange side?
So it's on the Jane Street side. The exchange net, I actually don't know what the exchange network looks like.
Yeah, the exchanges keep all of that behind, sort of their abstraction boundary, and they try really hard to make it, to give the same service to everyone.
And if money's no issue, why is the Jane Street side heterogeneous? Why not make it a homogeneous? All interfaces are identical. Choose the best.
I think that was in the paper. So I think it's.
I mean, I guess we just practically, right? It's really hard to deploy whole new infrastructure. So we've got many different generations going at once, but also, different applications have different, ideas.
So just after that, I think it's also like it's definitely in the paper, so I can say this, but it's if you think about sort of the gateway to the exchange, right? Like if you design this as a flow network, well, your hops, you're basically going through all of the servers are going to see like the same number of hops, right? And that may not be desirable if like you are you've designed the system in a way so that like one thing needs to get this packet as soon as possible. And so you might think about like how you can design this so that like there are some servers which are more proximate. And so I would this is in the paper, so I think they share a lot of interesting details.
I don't want to get into second order details, but long time ago, I used to work with the New York Stock Exchange and their networking infrastructure. Why is it that the financial side is very powerful with a lot of money and is able to do a lot of cool upgrades? The exchange is so poor and their network infrastructure is so primitive compared to some of the other things that on a relative scale of the kind of money being thrown for certain optimizations, 1/1000th or 1/10,000th of that money is being thrown on the other side. They do maintain a lot of fairness, but it's not like the infrastructure is anywhere even close. Any idea?
I think Andy would have a sort of definitive answer to that, but I would say like there's this one anecdote which I heard from NINES', which was that your exchange is like it's a one use server, right? Like you can run the entire exchange on like one box, and so like you don't actually need anything fancier. In fact, like the more complexity you add, the more the more intellectual work you have to do to worry about, oh, what happens if what happens to, how does this affect like your fairness, how does it affect your like latency equalization and all of that, right? And so you're better off just like sticking one box and then sending and then using that as your engine versus trying to do like some like fancy topology when like now you have to worry about like having artificially created asymmetry or like not yeah. So basically, simplicity is like virtue in this sense because it just works. You can just like run everything.
I mean, we read all these papers on network configuration and so on as an example. And one example I use in my class is there are times when if a network engineer leaves the exchange and a new network engineer comes, the new network engineer has no clue about 80% of the firewall rules that are written by the previous engineer, that they just leave it just like that. And it stays like that for 20 years, 10 years. And the state of networking is quite primitive with respect to how they actually architect a bunch of things. And compared to what is being thrown on this side of the river, the other side of the river seems very, very behind the curve.
So we're over time and we're cutting into the social event. Any last burning questions or comments? Okay, thanks, Devon. Just in closing, I'll make this quick. Just thank you everybody for coming. Highly appreciated. Maybe we'll send out a survey, what you think. Also useful feedback to get to Panda and the steering committee. Thanks again to Jane Street for hosting. Very, very much appreciated. And I don't know, Andy, do you want to make any closing remarks?
Yeah, happy hour. Helpers is right across the street. Easy to get to.
Okay.
So if Panda asks any questions, just say we discussed a lot of papers.
Is that a requirement?